There was no space, there was no time, there wasn't even darkness because darkness is something, and before 13.8 billion years ago something had not been invented yet. And then, for reasons no physicist on Earth can fully explain, everything that has ever existed, everything that ever will exist, exploded into being from a state so profoundly empty that calling it nothing doesn't even begin to capture what it was. This is not a metaphor. This is not philosophy. This is the single most unsettling fact modern science has ever confirmed. The universe, all 2 trillion galaxies of it, all the stars and planets and the atoms in your body right now, came from a fluctuation smaller than the period at the end of this sentence, a quantum hiccup in a void that shouldn't have been able to hiccup. And the deeper physicists look into that moment, the less sense it makes. Lawrence Krauss, one of the most controversial voices in cosmology, has spent decades arguing that a universe from nothing isn't just possible, it's inevitable. Stephen Hawking proposed that asking what came before the Big Bang is like asking what lies south of the South Pole, a question so broken by its own logic that it destroys itself. And yet we keep asking it. Because 13.8 billion years ago, during a window of time so brief it makes a nanosecond look like an eternity, something happened. Time itself was born. Space began to exist. And in the span of 10 to the negative 43 seconds, reality went from a seething quantum foam to the scaffolding of everything you've ever known. So how does existence begin when there's nothing to begin from? How does time start ticking when there's no clock, no space, no stage for it to happen on? And why, after a century of probing this question with every tool science has, does the answer only get stranger? This is that story. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. There is a question that breaks every tool we have for understanding reality. It sits at the edge of all science, all philosophy, all religion, and it refuses to behave. The question is simple. What came before? Before the universe? Before space? Before time itself? What was there? And the moment you try to answer it, language starts to fail. Your brain starts to stall. Because every word you reach for to describe the answer was invented inside a universe that already existed. You want to say there was nothing, fine. But where was that nothing? If there was no space yet, what container held the emptiness? You want to say it happened before everything began. But if time did not exist, what does the word before even mean? Before is a time word. It assumes a sequence, first this, then that. But if there was no time, there was no first. There was no then. There was no duration in which nothing could sit around being nothing. You're trying to describe a state that has no location, no moment, and no properties. And you're trying to do it with a language built entirely out of locations, moments, and properties. This is not a small problem. This is the problem, and it is exactly where cosmology, the science of the universe's origin, has to begin. Not with an answer, but with the acknowledgement that the question itself might be broken. For most of human history, the question did not seem broken. It seemed profound, but answerable. Every culture on Earth invented a story to fill the gap. In the beginning, there was a void, or a cosmic egg, or a god floating in an infinite ocean, or a dreaming giant whose body became the world. The details changed, but the structure was always the same. First, there was something like nothing. Then something happened, and after that, everything else. These stories worked because they gave people a place to stop asking. You could take the story on faith, or you could argue about which version was correct, but either way the framework held. There was a before, and it had contents, and those contents set the universe in motion. Then science arrived and started measuring things. By the 20th century, astronomers had noticed something deeply strange. Galaxies were moving, not drifting randomly, but fleeing. Every galaxy they looked at, in every direction, was rushing away from every other galaxy. The farther away a galaxy was, the faster it appeared to be receding. In 1929, Edwin Hubble published the observation that would eventually carry his name. The universe was not static. It was expanding. If the universe is expanding now, that means it was smaller yesterday, smaller last year, smaller 1 million years ago. You can run the math backward, rewinding the expansion like a film in reverse, and everything in the universe, all the galaxies, all the stars, all the matter and energy and space itself, converges on a single point. A point of infinite density and infinite temperature, where the known laws of physics collapse into nonsense. That point is not a place. It is not a moment you could visit with a camera. It is the limit of what the equations allow you to describe, and it sits roughly 13.8 billion years in the past. 13.787 billion years, if you want the number that the Planck satellite gave us, plus or minus 20 million years. That is the age of the universe. That is how long it has been since the expansion began. But notice what that number does not tell you. It does not tell you what the universe expanded from. It does not tell you why it started expanding. And it absolutely does not tell you what, if anything, was there before the expansion began. Scientists are careful about this. NASA's own description of the Big Bang is blunt. Scientists do not know what came before inflation or what powered it. They do not know because the math stops working. You can model the universe back to a fraction of a second after the expansion started, back to temperatures of 10 billion degrees Celsius, back to when the entire observable cosmos was smaller than an atom. But you cannot model it all the way to zero. At some point, the equations fill with infinities, and infinities in physics are a polite way of saying, we do not know what we are talking about anymore. So the question remains, what came before? And this is where the trouble with the word nothing really begins. When most people hear the word nothing, they picture a void, an empty room, deep space, a blank screen, the absence of things. But that kind of nothing still has properties. It has space, it has duration, it has dimensions you could measure if you had a ruler. A vacuum in the everyday sense is not nothing. It is something with all the objects removed. The air is gone, the furniture is gone, but the room is still there. Space is still there. Time is still there. You're still inside a universe. That is not the nothing we are talking about. The nothing that might have preceded the universe is not a container waiting to be filled. It is not a stage waiting for actors. It is the absence of the stage, the absence of waiting, the absence of absence itself if you want to go in circles for a while. Philosophers have been chewing on this for centuries. Leibniz asked why there is something rather than nothing, and considered it the deepest question in metaphysics. Heidegger spent whole books circling the concept of nothingness, and concluded that trying to think about it directly was like trying to grab smoke. You can point at where it was, but the moment you close your hand, there is nothing there to hold. The problem is that human consciousness is built to navigate a world of objects and events. Your brain is a pattern recognition machine fine-tuned by millions of years of evolution to track animals, predict weather, and avoid falling off cliffs. It is extremely good at that. It is not good at imagining the absence of existence itself. You cannot picture it, you cannot analogize it, you cannot even think about it without smuggling in some kind of framework, some background, some faint notion of space or time or possibility. And the moment you do that, you're not thinking about nothing anymore. You're thinking about something very empty. This is not just a philosophical problem, it is a scientific one. Because when physicists try to describe the origin of the universe, they keep running into the same wall. They need a starting condition. They need to say what the universe was like at the earliest moment they can model. And whatever they say, it will not be nothing in the absolute sense. It will be something. In the standard model of cosmology, the one built on decades of observation, and confirmed again and again by satellites like WMAP and Planck, the earliest describable state of the universe is not empty. It is almost the opposite. It is unimaginably dense, unimaginably hot, and filled with energy. The Big Bang was not an explosion into empty space. It was the expansion of space itself, carrying energy and matter along with it. Before that, and we're talking about the first fractions of a second here, there was a period called inflation when the universe expanded faster than light. Not because anything was moving through space faster than light, but because space itself was inflating. The rulers were stretching. During that instant, quantum fluctuations, tiny random ripples in the energy field, got blown up to cosmic size. Those ripples eventually became the seeds of galaxies. You can still see their fingerprints in the cosmic microwave background. The oldest light in the universe, emitted when the cosmos was only 380,000 years old. So the universe, in its earliest scientifically accessible moments, was not nothing. It was something incredibly specific. a state governed by quantum mechanics, inflation, and whatever field or force was driving the expansion. NASA puts it carefully. It is possible that energy during this period was just part of the fabric of space-time, not an object in space, not an event in time, but the thing that space and time were made of. If that sounds like a cheat, like scientists are just renaming the problem, you are not wrong. But it is an honest cheat. What they are saying is that the question, what came before, might not have an answer, because before is a concept that only makes sense inside time, and time itself might be a feature of the universe, not a container the universe sits inside. Imagine asking what is north of the North Pole. The question sounds reasonable. You can point north from anywhere on Earth, but if you are standing at the pole itself, the concept stops working. Every direction is south. North does not exist there, not because the maps are broken, but because you have reached the boundary where the framework no longer applies. The beginning of time might be the same kind of boundary, not a wall you crash into, but a point where the question itself stops meaning anything. This is where cosmology starts to blur into something more uncomfortable. Because if the universe does not require a before, if time itself began with the Big Bang, then the word nothing loses its foothold. You cannot point to a moment when nothing existed because moments are made of time, and time did not exist yet. You cannot point to a place where nothing was because space did not exist yet either. The closest you can get is to say that the universe emerged from a state that had no duration and no extent. A state that was not a state, a place that was not a place. And if you are feeling dizzy reading that, good, you should be. Your brain is doing exactly what it is supposed to do, which is reject the sentence as nonsense. But the universe does not care whether the sentence makes sense. It is here. You are here. Something happened. And whatever that something was, it did not need permission from human language to occur. Some physicists have tried to redefine nothing in a way that makes the question workable. Lawrence Krauss, a theoretical physicist, wrote a book called A Universe from Nothing, where he argued that the quantum vacuum, the lowest energy state allowed by the laws of physics, is as close to nothing as you can get. And that vacuum is not empty. It seethes with activity. Particles pop into existence and annihilate each other constantly. Energy fluctuates. The vacuum has weight. It bends space-time. It can, under the right conditions, inflate into an entire universe. Krauss is careful to say that this is not nothing in the philosophical sense. It is nothing in the physical sense. It is the absence of stuff, but not the absence of rules. The laws of quantum mechanics are still running. Space-time is still a thing. You're still inside a framework. But he argues that this is the only kind of nothing science can talk about. Anything more absolute is outside the reach of experiment and therefore outside the reach of science. Philosophers were not thrilled with that definition. They pointed out that if your nothing includes quantum fields and space-time and physical law, then it is not really nothing. It is a very minimalist something. And the question just moves one step back. Where did the quantum fields come from? Why those laws and not others? You have not escaped the problem, you have just rephrased it. But Krauss would say that is fine. Science does not promise to answer every question. It promises to answer the questions that can be tested, and the origin of physical law might not be one of them, at least not yet. There is another approach, quieter and stranger, that tries to dissolve the problem a different way. Some cosmologists have proposed models where the universe has no beginning at all, not because it is infinitely old, but because time is curved in such a way that there is no edge. Stephen Hawking called this the no-boundary proposal. Imagine the surface of a sphere. You can walk anywhere on it, and you will never hit a wall or fall off the edge. There is no beginning to the surface of a sphere. There is just surface. In Hawking's model, space-time might be shaped the same way. It is finite but boundless. The Big Bang is not a starting point. It is more like the South Pole on a globe, a place where certain coordinates converge but not a place where the surface begins or ends. In that picture, asking what came before the Big Bang is like asking what is south of the South Pole. The question assumes a direction that does not exist. If that model is right and no one knows if it is, then there was no nothing. There was no before. There was only a universe with a particular shape, and we happen to live in the part of that shape where time has a direction and events unfold in sequence. But the shape itself does not need a cause. It just is. That might sound like a cop-out. It might sound like giving up. But it is worth remembering that the universe does not owe us intuitive answers. It does not owe us stories that feel satisfying. It does not care whether our language can handle the truth. Here is what we know for certain. The universe has been expanding for 13.8 billion years. We can trace that expansion backward to a state of extreme density and heat. We can model the physics of that state with enormous precision, down to fractions of a second after it began. And then the models break, we hit a limit where the math stops giving answers. Everything before that limit, if before even applies, is speculation. Not wild speculation, informed speculation built on quantum mechanics and general relativity and decades of observation. But speculation nonetheless. The most honest thing a scientist can say about what came before the universe is this: we do not know. We might never know. The question itself might be unanswerable, not because we're not smart enough, but because the question is aimed at a target that does not exist, and yet the question will not go away. Because every time you look at the night sky, every time you think about where you came from, the question is there, waiting. If the universe had a beginning, what began it? If it did not have a beginning, why is there something instead of nothing? And what does nothing even mean? These are not just abstract puzzles. They are the foundation of everything else. Because before you can ask how the universe works, you have to ask why there is a universe at all. And before you can ask that, you have to figure out what you mean by nothing. So that is where we start. Not with an answer, but with the recognition that the question is harder than it looks. That the word nothing is not as empty as it seems, and that the universe, whatever it is, did not wait for us to understand it before deciding to exist. Now we go deeper. Because if nothing is not really nothing, if the void is not really empty, then what is it? What lives in the space between space, in the gap before time? The answer, if you can call it that, does not come from philosophy. It comes from the smallest scale of reality we have ever measured. It comes from the quantum foam. Empty space is not empty. That sentence sounds like the kind of fortune cookie wisdom someone would print on a motivational poster and sell at an airport gift shop. The sort of phrase that means everything and nothing at the same time. Except in this case, it is not wisdom. It is measurement. It is what happens when you point the most sensitive instruments humanity has ever built at the vacuum of space and ask what is actually there. The answer comes back wrong. Not wrong in the sense that the instruments are broken, but wrong in the sense that the vacuum refuses to behave like a vacuum. It hums, it vibrates, it flickers with activity that should not exist. Particles appear where there should be nothing and vanish before you can count them. Energy pulses in and out of existence on timescales so short that calling them brief is an insult to the word. The void, it turns out, is full. Not full of things you can hold or see or weigh on a scale. Full of potential, full of motion, full of events that happen so fast and at such a small scale that they slip through the cracks of ordinary reality like water through a sieve. Physicists have a name for this. They call it quantum foam. And once you understand what it is, the question of how a universe could emerge from nothing stops sounding like philosophy and starts sounding like plumbing. The story begins in 1955, though the groundwork was laid decades earlier. A physicist named John Archibald Wheeler, working at Princeton, was trying to understand what space and time would look like if you zoomed in far enough. Not telescope far, not microscope far, farther than that. Down past atoms, past protons, past quarks, all the way to the smallest distance that has any meaning in physics. That distance is called the Planck length. It sits at about 1.6 times 10 to the negative 35 meters. If you want to picture how small that is, imagine taking a meter stick and dividing it into 1 billion pieces. Then take one of those pieces and divide it into 1 billion pieces again. Then do that 2 more times. You are still not close. The Planck length is to the size of a proton what a proton is to the size of a solar system. It is not a distance you measure with rulers. It is a distance you calculate from the fundamental constants of the universe, from the speed of light, from gravity, from the quantum scale itself. And at that scale, Wheeler realized, space does not behave the way it does on the scales we are used to. It does not sit still. It does not form a smooth background for events to happen on. It writhes. It bubbles. It churns like the surface of boiling water, except the water is space and time themselves. Wheeler called it quantum foam, and the name stuck because no better metaphor has ever been found. Picture the foam on top of a freshly poured beer. Up close, it is a mess. Bubbles forming and popping, edges blurring into each other, nothing stable, nothing smooth. Pull back far enough and the foam looks like a solid surface. Sit at the bar and the beer looks calm. But zoom in with a microscope and you would see chaos. Quantum foam is the same idea applied to the fabric of reality itself. At the Planck scale, space-time is not a stage, it is a storm. The reason this happens comes down to one of the strangest and most ironclad rules in physics. It is called the Heisenberg uncertainty principle, and it was discovered in 1927 by a German physicist named Werner Heisenberg while he was trying to figure out why electrons refuse to behave themselves. The principle says, in plain language, that there are pairs of properties in nature that cannot both be known precisely at the same time. The more accurately you measure one, the fuzzier the other becomes. Position and momentum are the famous pair. If you know exactly where a particle is, you cannot know exactly how fast it is moving. If you know its speed perfectly, its location becomes a blur. This is not a limitation of your instruments. It is not a problem that better technology will fix. It is baked into the structure of reality. The universe itself does not allow both facts to exist with perfect clarity at the same instant. And here is where it gets interesting for the vacuum. There is another pair of quantities that obey the uncertainty principle: energy and time. If you look at a very short interval of time, the amount of energy present during that interval becomes uncertain, fuzzy, undefined. And that fuzziness is not small. The shorter the time window you examine, the larger the energy uncertainty becomes. At the Planck timescale, about 10 to the negative 43 seconds, the uncertainty is enormous, big enough to create particles, big enough to bend space-time, big enough to make the vacuum itself unstable. Think of it this way. Imagine you are trying to take a photograph of a highway from an overpass, but your camera shutter is stuck open for a full minute. During that minute, hundreds of cars pass beneath you. When you develop the photo, the highway looks blurry, filled with streaks of light, nothing sharp, nothing clear. But if someone asks you how many cars were on the highway at exactly the 30th second, you cannot answer. The image does not have that information. The cars were there, but the long exposure smeared them into noise. Now imagine the opposite. Your shutter is open for 1/1,000,000th of a second. You snap a photo and the image is sharp, but now you cannot tell how fast the cars were moving. They look frozen. Their speed has become uncertain because you did not give yourself enough time to measure it. Energy and time work the same way. Measure energy over a long period and you get a precise value. Measure it over a very short period and the energy starts to blur. And if the period is short enough, the blur gets so large that particles can appear out of nowhere, exist for a fraction of a second, and then vanish before the universe notices they were ever there. These are called virtual particles, and they are everywhere. Right now, as you read this, the space in front of your face is filled with them. Electron and positron pairs flickering into existence and annihilating each other in less time than it takes light to cross the width of a proton. Photons appearing and disappearing. Quarks and antiquarks doing the same. They do not last long enough to be detected directly, but they are real enough to have measurable effects. And those effects show up in experiments with a precision that borders on the absurd. One of the cleanest examples is something called the Casimir effect, first predicted in 1948 by a Dutch physicist named Hendrik Casimir. He was studying how quantum fluctuations in the vacuum would behave near metal surfaces, and he realized something strange. If you take two uncharged metal plates and place them very close together in a vacuum, the quantum fluctuations between the plates are different from the fluctuations outside the plates. The plates act like filters. They block certain wavelengths of virtual particles from forming in the gap between them. But outside the plates, all wavelengths are still allowed. The result is a pressure difference. The vacuum outside pushes harder than the vacuum inside, and the plates are forced together by a measurable amount. That is not a metaphor. You can do this experiment in a lab. You can measure the force. And when you do, the numbers match the predictions from quantum field theory to ridiculous precision. The vacuum, which should be empty, is pushing on objects hard enough to move them. And the only way to explain that is to admit that the vacuum is full of fluctuations that behave exactly the way the math says they should. The other example is even more impressive. The electron, one of the most basic particles in nature, has a magnetic property that physicists can measure with extraordinary accuracy. When you calculate what that magnetic property should be using quantum field theory, taking into account all the virtual particles that pop in and out of existence around the electron, the theory and the experiment agree to 12 decimal places. 12. That is like predicting the distance from New York to Los Angeles to within the width of a human hair. You do not get that kind of agreement by accident. You get it because the theory is describing something real, even if that something is invisible and short-lived and utterly unlike anything you will ever encounter in daily life. So the vacuum is not empty. It is a roiling sea of quantum activity, a froth of particles and antiparticles constantly being created and destroyed, borrowing energy from the uncertainty principle and paying it back before the bill comes due. Physicists call this the quantum vacuum, and it is as close to nothing as the universe allows. But it is not nothing in the way most people think of the word. It is not silent. It is not still. It is not a blank slate. It is the lowest energy state permitted by the laws of physics, and even that state is busy. John Wheeler understood this, and he pushed the idea further than most of his peers were comfortable with. He asked what would happen if you looked at space-time itself at the Planck scale, not just the particles moving through it, but the geometry of space and time. And the answer, according to the math, was that space-time would not be smooth. It would be full of fluctuations, tiny wormholes opening and closing, regions where space curved in on itself and then relaxed, bits of topology appearing and disappearing like bubbles in a pot of boiling water. He called it space-time foam, and he argued that at the Planck length, the whole notion of a fixed geometric stage breaks down. Space and time themselves become quantum objects, subject to the same uncertainty, the same flickering existence as the particles they contain. This is not easy to picture. Your brain wants space to be a container, a box that things happen inside. But at the smallest scales, the box is made of the same quantum stuff as everything else. The container and the contents blur together. You cannot point to a place and say this is where space is because space itself is fluctuating. You cannot point to a moment and say this is when it happened because time is fluctuating too. The whole framework wobbles, and if you rewind the history of the universe back to the very first moment, back to the Planck era when the cosmos was only 10 to the negative 43 seconds old, you are not dealing with a universe that looks like a smooth ball of fire. You are dealing with a universe made of quantum foam, a state where space and time are so violently uncertain that the idea of a fixed geometry does not apply, a state where the words here and now stop working. Some models describe this era as a churning soup of Planck-scale black holes, each one about 10 to the negative 35 meters across, appearing and evaporating in a flash, pulling space-time into knots, and then releasing it. That is not a literal description. Nobody has seen a Planck-scale black hole, nobody ever will, but it is a way of making sense of what the equations are saying, which is that at the smallest scales, gravity and quantum mechanics fight each other for control of reality, and neither one wins cleanly. The result is chaos. The result is foam. And here is the thing that makes this relevant to the origin of everything. The quantum vacuum is not passive. It does not just sit there fluctuating for no reason. Under the right conditions, those fluctuations can grow. They can inflate. They can become real in the sense that they stop borrowing energy and start keeping it. A virtual particle that normally would vanish after 10 to the negative 23 seconds can, if the surrounding conditions allow it, stabilize and persist. A ripple in space-time that normally would collapse back into the foam can, if something gives it a push, expand and become a permanent feature of the geometry. The vacuum, in other words, can give birth to things that last. And if you're willing to follow that line of reasoning all the way to its conclusion, you arrive at a deeply strange idea. The entire universe might be one of those fluctuations, a quantum event that started in the foam, inflated beyond the point of no return, and became the cosmos we live in. Not because something outside the vacuum created it, but because the vacuum itself is unstable. Because empty space, when you look closely enough, refuses to stay empty. Lawrence Krauss, a theoretical physicist at Arizona State, has argued this point more publicly than almost anyone. In his book A Universe from Nothing, he makes the case that the quantum vacuum is the only kind of nothing that science can meaningfully discuss. And in that vacuum, the laws of quantum mechanics are always running. Particles are always fluctuating. Energy is always uncertain. You do not need an external cause to get something from this kind of nothing. You just need the right conditions for a fluctuation to grow. And once it grows past a certain threshold, it stops being a fluctuation and starts being a universe. Philosophers objected. They said this was not really nothing because the quantum vacuum still has rules. It has structure. It has space and time. even if those things are foamy and uncertain. Krauss responded that this is the only nothing physics can address. Anything beyond that, any kind of absolute metaphysical void, is outside the reach of experiment and therefore outside the reach of science. He is not wrong. You cannot design an experiment to test what reality would look like without rules. Rules are what let you do experiments in the first place. So if you want to ask how the universe began, you have to start with something, and the quantum vacuum is the closest to nothing that still allows for a story. This does not mean the vacuum explains everything. It does not tell you why the laws of quantum mechanics exist in the first place. It does not tell you why the universe has 3 dimensions of space and one of time instead of 5 and 2, or 10 and 0. It does not explain why the constants of nature have the values they do. Those questions are still open. But what the quantum vacuum does is remove one layer of mystery. It shows that you do not need a miracle to get a universe started. You do not need a hand reaching in from outside to light the fuse. You just need a vacuum that obeys quantum rules, and the fluctuations take care of the rest. The visual metaphor Wheeler gave us has held up for 70 years because nothing better has replaced it. Foam, a froth of activity at the smallest scales invisible to us, irrelevant to our daily lives but foundational to everything that exists. You cannot smooth it out. You cannot turn it off. It is what space and time are made of when you zoom in past the point where classical physics applies, and it is seething, always, everywhere, even in the deepest voids of intergalactic space, even in the emptiest laboratory vacuum chambers on Earth. The foam is there, ticking away, creating and destroying, borrowing and repaying, holding the baseline of reality just above the level of absolute nothing. And if you're wondering whether this is speculation or science, the answer is both. The foam itself has never been observed directly. You cannot take a picture of it. The scales are too small, the timescales are too short, but the effects are observable. The Casimir effect is real. The electron's magnetic moment is real. The predictions that come from assuming the vacuum is full of quantum fluctuations match the experiments to a degree that makes coincidence statistically impossible. So while we cannot see the foam, we can see its fingerprints. And those fingerprints are everywhere. This is the foundation. This is the substrate. This is what lies beneath the surface of the universe when you peel back the layers far enough. Not a void, not a stillness, not a blank page waiting for the first word. A churning, energetic, restless state that has no off switch and no pause button. A state that, at the right moment, under the right conditions, could swell into something much larger. Something with stars and galaxies and people asking questions about where it all came from. The quantum foam does not answer every question, but it redefines the starting point. It tells you that the universe did not need to come from nothing in the absolute sense. It only needed to come from the lowest energy state that the laws of physics allow. And that state, strange as it sounds, is not empty. It never was. Now the question shifts. If the foam is the substrate, the baseline, the closest thing to nothing that still exists, then when did it become something more? When did the fluctuations stop being temporary and start being permanent? When did space and time themselves stop being foam and start being geometry? That transition has a name. Physicists call it the Planck era, and it is where the universe, in any recognizable sense, begins. Now the question shifts. If the foam is the substrate, the baseline, the closest thing to nothing that still exists, then when did it become something more? When did the fluctuations stop being temporary and start being permanent? When did space and time themselves stop being foam and start being geometry? That transition has a name. Physicists call it the Planck era, and it is where the universe, in any recognizable sense, begins. The Planck era is not a place. It is not an event you could witness if you had a time machine and a very good insurance policy. It is a boundary, a line drawn in the sand of mathematics where the equations physicists use to describe reality stop giving sensible answers and start spitting out infinities and contradictions. Cross that line and you are in a realm where space and time, the two most fundamental concepts we have for organizing experience, lose their meaning entirely, or at least they lose the meaning we're used to. What they become on the other side of that line is a question that has occupied some of the best minds in physics for half a century, and the honest answer is that nobody knows. Here is what we do know. The Planck time is 5.39 times 10 to the negative 44 seconds. That is a decimal point followed by 43 zeros and then a 5. If you want a sense of how short that is, consider this. Light, the fastest thing in the universe, travels about 300,000 kilometers in 1 second. In 1 Planck time, light travels 1 Planck length, which is about 1.6 times 10 to the negative 35 meters. A proton, one of the smallest objects we have ever measured, is about 10 to the negative 15 meters across. The Planck length is 20 orders of magnitude smaller than that. If you scaled a proton up to the size of the observable universe, the Planck length would still be smaller than a human hair. We are not talking about small in the everyday sense. We are talking about a scale so removed from human experience that language stops being useful, and you have to fall back on numbers that do not mean anything to your brain. And yet that absurdly tiny timescale is where the story begins. The Planck era is usually defined as the period from time 0, whatever that means, up to about 10 to the negative 43 seconds after the expansion started. Before that threshold, if before even applies, the universe was in a state that current physics cannot describe. Not because physicists are lazy or uncreative, but because the tools they have, general relativity and quantum mechanics, were not built to handle the conditions that existed at that moment. General relativity describes gravity and the large-scale structure of space-time. Quantum mechanics describes the behavior of particles and fields at the smallest scales. Both theories are extraordinarily successful within their domains, but they do not play well together. When you try to combine them, when you try to describe a situation where gravity is strong and quantum effects are dominant at the same time, the math breaks. You get infinities. You get predictions that make no sense. You get equations that refuse to give you answers. The Planck era is precisely that situation. A moment when the universe was so small and so dense that gravity and quantum mechanics were both in charge, and neither theory can tell you what happens when they meet. Astronomy magazine called the Planck scale the smallest unit of the universe we can describe, or perhaps that even exists. That second part is not settled. Some physicists think the Planck length really is the smallest possible distance, that space itself is fundamentally grainy at that scale, like pixels on a screen. Others think the Planck scale is just the limit of our current theories, and that something deeper is going on underneath. Either way, the result is the same. We cannot see past it. We cannot calculate past it. We cannot even define what the words see and calculate would mean past it. Wikipedia's summary of the Planck epoch is blunt. There is no currently available physical theory to describe such short times. That is not a complaint. That is a statement of fact. Physics stops working, the map ends, you are off the edge of the known world. So what was the universe like during the Planck era? The standard answer, repeated in textbooks and NASA summaries and popular articles, is that the universe was unimaginably hot and dense. Temperatures are estimated at above 10 to the 32 Kelvin, which is a number so large that it does not correspond to anything you have ever encountered. The core of the Sun sits at about 15 million Kelvin. The moment of a supernova explosion reaches a few billion Kelvin. 10 to the 32 Kelvin is a trillion times hotter than that. At those temperatures, matter as we know it does not exist. Atoms do not exist. Protons and neutrons do not exist. Even quarks, the building blocks of protons and neutrons, might not exist in any stable form. You're left with a soup of energy so violent that particles are constantly being created and destroyed, and the distinction between matter and energy blurs into irrelevance. Density is equally absurd. If you took all the mass in the observable universe and compressed it into a region the size of a single atom, you would still not be close to the densities present during the Planck era. Some estimates place the density at around 10 to the 93 grams per cubic centimetre. For comparison, water is 1 gram per cubic centimetre. Lead is about 11. The core of a neutron star, one of the densest objects in the modern universe, is around 10 to the 15. The Planck era is 78 orders of magnitude denser than that. You cannot build an intuition for that. You cannot picture it. You can only write down the numbers and trust that the math is telling you something real. And yet those numbers are not the strangest part. The strangest part is what they imply about the forces of nature. Right now, in the universe we live in, there are 4 fundamental forces. Gravity, which holds planets in orbit and pulls objects toward the ground. Electromagnetism, which governs light, electricity and chemistry. The strong nuclear force, which binds quarks into protons and neutrons and holds atomic nuclei together. And the weak nuclear force, which governs certain types of radioactive decay. These forces behave very differently from one another. Gravity is weak but acts over infinite distances. Electromagnetism is stronger but can be shielded. The strong force is extremely powerful, but only works at distances smaller than an atomic nucleus. The weak force is even more limited in range and only shows up in specific particle interactions. They are distinct, separate, each with its own rules. But the standard model of cosmology, built on decades of particle physics experiments and theoretical work, predicts that this was not always the case. At high enough energies, the forces begin to merge. Electromagnetism and the weak force are already known to unify at energies above about 100 GeV, which is a scale we have recreated in particle accelerators like the Large Hadron Collider. At that energy, the two forces stop being separate and become a single electroweak force. Physicists won a Nobel Prize for predicting that, and experimentalists won another for confirming it. It is not speculation, it is tested. The next step up is the strong force. Theoretical models, most of them variations on something called grand unified theories, predict that at even higher energies, around 10 to the 16 GeV, the strong force merges with the electroweak force into a single unified force. We have never tested that. We cannot. The energies required are millions of times higher than anything the LHC can produce. But the math suggests it happens, and the math has been right about enough other things that most physicists take it seriously. And then there is gravity. Gravity is the holdout. At the Planck energy, about 10 to the 19 GeV, gravity is expected to unify with the other three forces into a single overarching force that governed the universe before it cooled enough for the forces to split apart. That unification, if it happened, would have lasted only for the Planck era. Once the universe expanded and cooled past the Planck threshold, gravity separated first, followed by the strong force, followed by the electro-weak force, and finally electromagnetism and the weak force split into the four distinct forces we see today. It is a story of symmetry breaking, a story of a universe that started simple and became complicated as it aged. But here is the problem. Nobody knows how to write down the equations for that final unification. Gravity does not fit into the same mathematical framework as the other three forces. The other three are described by quantum field theory, a framework where forces are carried by particles and interactions happen in discrete packets of energy. Gravity is described by general relativity, a framework where force is not really a force at all, but a curvature of space-time itself. The two frameworks use different languages, different assumptions, different mathematical structures, and when you try to force them together, the result is nonsense. You get predictions that blow up to infinity. You get quantities that should be finite, but turn out to be undefined. You get a theory that cannot make predictions, which means it is not really a theory at all. This is the problem of quantum gravity, and it is the single biggest unsolved problem in theoretical physics. There are candidates. String theory is one. It proposes that the fundamental building blocks of reality are not particles, but tiny vibrating loops of energy, and in that framework gravity emerges naturally alongside the other forces. Loop quantum gravity is another. It suggests that space-time itself is made of discrete chunks, like a fabric woven from threads, and that at the Planck scale those threads become visible. Both ideas are mathematically sophisticated, both have passionate supporters, neither has been confirmed by experiment, neither has made a prediction we can test with current technology. They are for now frameworks, possibilities, best guesses built on elegant mathematics, and the hope that nature cares about elegance. So when cosmologists talk about the Planck era, they are not describing a moment they fully understand. They are describing the boundary where understanding stops. The era is defined not by what we know, but by what we do not. And one of the things we do not know is whether space-time, the stage on which all events occur, even existed in a recognizable form during that era. Some models suggest that space and time are emergent properties, that they arise from something more fundamental, that in the Planck era the universe was in a pre-geometric state, a condition where the concepts of here and now had not yet solidified. John Wheeler, the same physicist who coined the term quantum foam, speculated about this. He called it a state of superspace, a kind of metageometry where all possible shapes and configurations of space-time coexist in a quantum superposition. And only after the Planck era does one particular geometry, the one we live in, become real. That idea sounds like science fiction, and maybe it is, but it is not obviously wrong. If space-time is made of quantum foam at the smallest scales, and if the Planck era is when the universe was small enough that those scales dominated everything, then space-time itself would have been foamy, uncertain, undefined. You could not point to a location and say this is where the Big Bang happened, because location is a concept that only makes sense when space is smooth and well behaved. You could not point to a moment and say this is when it started, because time, as a measurable sequence of events, might not have existed yet. The Planck era might not have been a moment in time. It might have been the process by which time itself came into being. This is where the phrase "before time existed" starts to make sense, though it is still a slippery phrase. Most popular accounts of the Big Bang say that time began at the Big Bang, that asking what came before is like asking what is north of the North Pole. That metaphor comes from Stephen Hawking, and it is useful, but it is also a simplification. What physicists actually mean is that time as we experience it, time as a smoothly flowing dimension with a past and a future, only makes sense after the Planck era. Before that, or during that, depending on how you phrase it, time was not a clear concept. It was mixed up with space. It was fluctuating, it was part of the foam. The universe did not have a clock because the universe was too small and too chaotic for clocks to mean anything. And yet something happened. That much is clear. The universe transitioned from a state where space-time was foam to a state where space-time was geometry, from a state where the four forces were unified into a state where they were distinct, from a state with no measurable size to a state that was expanding. That transition is the Planck era. Not a single event, but a process, a threshold. The moment when the universe cooled and expanded just enough for the laws of physics as we know them to start applying. Gravity separated first. The equations of general relativity became valid. Space-time became a thing you could describe with coordinates and distances and durations. And once that happened, once space-time solidified, the rest of the story could begin. How long did this take? 10 to the negative 43 seconds. Less time than it takes light to cross a distance smaller than any particle we have ever observed. It is not a duration you can experience. It is not a duration you can imagine. But it is, according to the best models we have, the duration during which the universe went from a state we cannot describe to a state we can. From a singularity, or something like a singularity, to a hot, dense, expanding cosmos governed by rules we recognize. That is the Planck era. The boundary, the threshold, the instant when time itself was forged. The word singularity comes up a lot in popular descriptions of the Big Bang, and it is worth pausing on what that word actually means. In mathematics, a singularity is a point where a function blows up, where the numbers stop making sense. In general relativity, a singularity is a place where space-time curvature becomes infinite. The center of a black hole is a singularity. The Big Bang in the equations of general relativity run backward to time zero is also a singularity. All the mass and energy of the universe compressed into a point with zero volume and infinite density. That is what the math says. But physicists are quick to point out that this is almost certainly not what actually happened. The singularity is an artifact of the theory. It is what you get when you use general relativity in a regime where general relativity is not valid. It is the equation's way of telling you that something else is going on, something the equation cannot capture. Quantum mechanics, the other pillar of modern physics, does not allow true singularities. Quantum mechanics puts limits on how precisely you can localize energy and matter. It introduces uncertainty. It smooths out the infinities that general relativity produces. So most physicists expect that when we finally have a working theory of quantum gravity, the singularity will disappear. It will be replaced by something else. Maybe a region of Planck-scale foam. Maybe a bounce, where the universe contracts to a minimum size and then expands again. Maybe a superposition of geometries, where the very idea of a single definite state breaks down. We do not know. But the singularity as a literal point of infinite density is probably not the right picture. It is a placeholder, a signpost that says the real story is more complicated than we can currently describe. And yet the Planck era, singularity or not, marks the earliest moment we can talk about with any confidence. After 10 to the negative 43 seconds, the universe had a temperature. It had a size. It had forces that behaved in predictable ways, or at least ways we can model with equations that work. The foam had settled, or begun to settle, into something more structured. Space-time was no longer a seething chaos of quantum uncertainty, but a smooth, expanding manifold with a well-defined geometry. Time flowed. Space stretched. Events happened in sequence. The universe, in other words, had become a universe. What comes next is a story of expansion and cooling, a story of phase transitions where the unified forces split apart and particles gained mass and the first stable structures began to form. But none of that could happen until the Planck era was over, until the universe had crossed the threshold where physics as we know it starts to apply. That crossing is not dramatic. There is no explosion. There is no sound. There is only a shift, invisible and instantaneous, from a state that defies description to a state that permits it. From a moment where the question "what is happening" does not have an answer to a moment where it does. And it is during that shift, during that impossibly brief window, that time itself emerged. Not time as an abstract concept, but time as a measurable dimension. Time with a direction. Time with a past and a future. Before the Planck era, if before even makes sense, time was part of the foam. It was quantum. It was uncertain. It was tangled up with space in ways that make the word sequence meaningless. After the Planck era, time had untangled. It had become something you could measure with a clock if clocks had existed, which they did not. But the structure was there. The framework was in place. The universe had a past, even if that past was only 10 to the negative 43 seconds old. This is what physicists mean when they say time began at the Big Bang. Not that there was a moment when a switch flipped and time turned on, but that there is no way to talk about time before the Planck threshold. The concept does not apply. The equations do not work. You're asking a question in a language that does not exist yet. And while that might sound like a dodge, like scientists refusing to answer the hard question, it is actually the most honest thing they can say. The Planck era is the edge of the map, the limit of the known, the place where the tools we use to understand reality stop giving answers and start giving noise. But the universe did not stop there. The Planck era ended, the foam settled, and what came next was even stranger. Because the universe, barely old enough to have a clock, was about to undergo a transformation so rapid and so violent that it would take a speck of quantum uncertainty and blow it up to the size of galaxies, faster than light, faster than anything. A moment of expansion so extreme that it earned a name of its own. Physicists call it inflation, and it is where the universe went from small to unimaginably large in less time than it takes to blink, in less time than it takes to think, in a duration so short that calling it an instant is being generous. The Planck era gave the universe time. Inflation gave it space. Enough space to hold everything you have ever seen or ever will see. And it did it in a flash. The Planck era gave the universe time. Time as a dimension. Time as a sequence. Time as something you could mark with a clock, even if there was no clock to do the marking. But time alone is not enough to build a cosmos. You also need space, a lot of it. Enough to hold trillions of galaxies scattered across distances so vast that light from some of them will never reach us no matter how long we wait. And the strange thing, the thing that bothered physicists for decades before anyone came up with a decent explanation, is that the universe got all that space very, very quickly. Not gradually. Not over billions of years of steady expansion. It got it in a flash. In less than a trillionth of a trillionth of a trillionth of a second, the universe went from smaller than a proton to roughly the size of a beach ball. Maybe larger. The numbers depend on which model you use and which assumptions you bake in, but the scale of the change does not. It is absurd, it is violent, and it is the only way anyone has ever figured out to explain why the universe looks the way it does. That flash has a name. Physicists call it inflation. And if you have heard of it at all, you have probably heard it described as the moment when the universe expanded faster than the speed of light. That description is technically correct, but it is also misleading. Nothing actually moved faster than light. No particle, no signal, no information. What expanded was space itself. The rulers stretched, the grid inflated. If you had been standing in one spot during inflation, which you could not have been because standing requires matter, and matter did not exist yet, you would not have felt like you were moving at all. But the spot next to you would have been racing away faster than light could ever catch up. Not because it was moving through space, but because space was growing between you. This is not a small detail. It is the entire point. Inflation did not push things apart, it made more space. space that did not exist a moment earlier, space that the universe did not borrow from anywhere because there was no anywhere to borrow from. It just appeared, and the amount that appeared is staggering. One estimate, repeated across textbooks and NASA briefings, says that by the end of inflation, the region that would become our observable universe had grown by a factor of at least 10 to the 26th. That is a 1 with 26 zeros after it. Start with something the size of a proton and multiply its diameter by that number, and you get something bigger than a galaxy. Start with a speck of quantum foam, and you get a universe. The question is why? Why would the universe do that? What possible mechanism could drive an expansion that extreme in a time window that short? And more to the point, why should we believe it happened at all? The answer to the first question is a hypothetical field called the inflaton. The answer to the second question is that without inflation, the universe we see makes no sense. Let's start with the problems. Before Alan Guth introduced inflation in 1980, cosmologists had a working model of the Big Bang that explained a lot. It explained why the universe was expanding. It explained why the cosmic microwave background radiation existed. It explained the abundance of hydrogen and helium. It was a good model, but it had cracks, big ones. And the more precisely astronomers measured the universe, the wider those cracks became. The first problem is called the horizon problem. When you look at the cosmic microwave background, the faint glow of radiation left over from when the universe was 380,000 years old, you see a pattern, a map of temperature fluctuations across the entire sky. And the strangest thing about that map is how smooth it is. The temperature in one patch of sky is almost exactly the same as the temperature in a patch on the opposite side of the sky. The difference is only a few parts in 100,000. That uniformity is what let the first stars and galaxies form. If the early universe had been much lumpier, gravity would have pulled everything into black holes before stars ever ignited. If it had been much smoother, nothing would have clumped together at all. The universe threaded a needle. It was smooth enough to allow structure, but not so smooth that structure never formed. The problem is that those two patches of sky, sitting on opposite sides of the observable universe, have never been in contact with each other. Not ever. Light from one has never reached the other. In the standard Big Bang model, without inflation, there is no time in the history of the universe when those two regions could have exchanged information. They are beyond each other's horizons, causally disconnected, and yet they have the same temperature to absurd precision. It is like finding two people on opposite sides of the planet wearing identical custom-made suits. And when you ask how that happened, they tell you they have never met, never spoken, and have no mutual friends. Coincidence stops being an acceptable answer at some point. You start looking for a cause. Inflation provides one. If the universe underwent a brief period of exponential expansion very early on, then regions that are now separated by billions of light years were once close enough to touch. They were in contact. They reached thermal equilibrium, meaning they settled into the same temperature. Then inflation blew them apart, stretching them to opposite sides of the sky faster than light could cross the gap. The uniformity was not a coincidence. It was a memory, a relic of a time when the whole observable universe fit inside a region smaller than the nucleus of an atom. The second problem is called the flatness problem. Space-time, according to general relativity, can be curved. It can curve positively, like the surface of a sphere, or negatively, like a saddle. Or it can be flat, like a sheet of paper stretched infinitely in all directions. Which one you get depends on the density of matter and energy in the universe. If the density is too high, the universe curves in on itself and eventually collapses. If the density is too low, the universe curves outward and expands forever, thinning out until nothing is left but cold, empty space. If the density is exactly right, sitting on a knife edge between those two extremes, the universe is flat. It expands forever, but the expansion gradually slows. Measurements of our universe, including data from satellites like WMAP and Planck, show that the universe is flat. Not approximately flat. Flat to within a fraction of a percent. That is strange because flatness is an unstable condition. Imagine balancing a pencil on its tip. If you get the angle exactly right, it will stand for a moment, but the tiniest deviation, the smallest vibration, and it falls. A flat universe is like that pencil. If the density at the moment of the Big Bang had been even slightly higher or lower, the universe would have curved dramatically within the first second. The fact that it is still flat today, more than 13 billion years later, means the initial conditions had to be tuned to absurd precision. The density at 1 second after the Big Bang had to match the critical value to something like 15 decimal places. That level of fine-tuning does not happen by accident. It demands an explanation. Inflation provides one. During the exponential expansion, any initial curvature gets stretched flat. Think of inflating a balloon. When the balloon is small, you can see the curve. Blow it up to the size of the Earth and the surface looks flat from where you're standing. Blow it up to the size of the observable universe, and you would need instruments capable of measuring distances across billions of light years to detect any curve at all. Inflation takes whatever shape the universe started with and flattens it by force. It does not require the initial conditions to be finely tuned. It tunes them itself. The third problem is more obscure but no less serious. Grand unified theories, the models that describe how the fundamental forces of nature merged at high energies, predict the existence of magnetic monopoles. These are hypothetical particles that carry a single magnetic charge, north without south, or south without north. Ordinary magnets always have 2 poles. Cut a bar magnet in half, and you get 2 smaller magnets, each with a north and a south. Monopoles, if they exist, would be different. They would be stable, massive, and produced in enormous numbers during the hot early universe, and we have never found one. Not a single confirmed detection. That is a problem. If the standard Big Bang model is right, and the universe went through a grand unified phase, monopoles should be everywhere. They should outnumber protons. The fact that we do not see them suggests either that grand unified theories are wrong, which most physicists doubt, or that something happened to dilute the monopoles to undetectable levels. Inflation does exactly that. If the universe expanded by a factor of 10 to the 26th or more, any monopoles that formed before inflation would be spread so thin that finding one would be like finding a specific grain of sand scattered randomly across the surface of a trillion Earths. So inflation solves 3 major problems in one swoop. It explains the uniformity of the cosmic microwave background, it explains why the universe is flat, and it explains why we do not see magnetic monopoles. That is a strong argument in its favour, but it is not proof. Proof requires a mechanism. You need to explain not just what inflation does, but how it does it. And that is where the inflaton field comes in. The inflaton is not a particle in the usual sense. It is a field like the electromagnetic field or the Higgs field that fills all of space and has a value at every point. Fields in physics are the fundamental objects. Particles are just ripples or excitations in those fields. The electron is a ripple in the electron field. The photon is a ripple in the electromagnetic field. The inflaton, if it exists, is a ripple in the inflaton field. Except during inflation, the field was not rippling. It was sitting at a high energy value, and that value, that energy density, is what drove the expansion. Here is how it works. In quantum field theory, fields can have potential energy, like a ball sitting on a hill. If the ball is at the top of the hill, it has a lot of potential energy. If it rolls down to the bottom, that energy gets converted into motion. The inflaton field, in the very early universe, was sitting at the top of its potential energy curve. It was in what physicists call a false vacuum, a state that looks stable, but is not the lowest energy state available. And while it sat there, its energy density acted like a kind of anti-gravity. Instead of pulling things together, it pushed space apart, not by moving objects through space, but by creating more space. The higher the energy density, the faster the expansion. And because the energy density stayed roughly constant as space expanded, the expansion was exponential. Each tiny fraction of a second, the universe doubled in size, then doubled again, over and over, faster than anything, until the field finally rolled down the hill and the energy got converted into particles and radiation. That final step is called reheating. During inflation, the universe was cold in the sense that there were no particles. There was only the inflaton field and the energy locked inside it. When the field decayed, that energy had to go somewhere. It went into creating matter and radiation, filling the newly expanded space with a hot, dense soup of particles. The universe went from empty and cold to packed and blazing in less time than it takes light to cross the width of an atom. That hot, dense state is what we usually think of as the Big Bang. The moment when the universe became something we can describe with normal physics. But inflation came first. The Big Bang was not the beginning, it was the reheating. The timing is almost absurd. Inflation is thought to have started around 10 to the negative 36 seconds after the Planck era ended, and lasted until about 10 to the negative 32 seconds. That is a span of time you cannot visualize. Light, traveling at 300,000 kilometers per second, moves about 3 times 10 to the negative 27 meters in that duration. A proton is about 10 to the negative 15 meters across. Light would not have time to cross the width of a quark, and in that infinitesimally short window, the universe grew by a factor that dwarfs anything you will ever encounter in daily life. A factor so large that if you started with a region the size of the Planck length and inflated it by the same amount, you would end up with something bigger than the observable universe today. One widely cited number says the observable universe's content began in a region with a radius of about 4 times 10 to the negative 29 meters and expanded to roughly 0.9 meters by the end of inflation, from smaller than a proton to the size of a basketball. That number comes from models that make specific assumptions about how long inflation lasted and how fast the field rolled, and different assumptions give different numbers. Some models stretch the universe to the size of a grapefruit. Some go bigger. The details matter for predictions, but the broad picture does not change. Inflation took something unimaginably small and made it large enough to contain everything you see when you look up at the night sky. And here is the part that makes inflation more than just a clever fix for cosmological problems. Inflation makes predictions, testable ones. The most important prediction has to do with the fluctuations in the cosmic microwave background. During inflation, quantum fluctuations in the inflaton field, tiny random ripples in the energy density, got stretched to cosmic size. Those ripples froze into the fabric of space, and when inflation ended and the universe filled with matter and radiation, those ripples became density variations. Regions that were slightly denser than average pulled in more matter and eventually became galaxy clusters. Regions that were slightly less dense became voids. The pattern of fluctuations you see in the cosmic microwave background today is a direct snapshot of those quantum ripples blown up to the scale of the universe. Inflation predicts that those fluctuations should be nearly scale invariant, meaning they should look roughly the same at all scales. It predicts that the universe should be flat, or very close to flat. It predicts a specific relationship between the size of the fluctuations and the geometry of space. And when satellites like COBE, WMAP and Planck measured the cosmic microwave background with increasing precision, the results matched the predictions. Not perfectly, because the models have adjustable parameters and the data has uncertainties, but closely enough that most cosmologists treat inflation as the leading explanation for why the universe looks the way it does. That does not mean inflation is proven. It is still a hypothesis, a very successful hypothesis, but a hypothesis nonetheless. The inflaton field has never been detected directly. We do not know what it is made of or how it relates to the other fields in the standard model of particle physics. We do not know for certain when inflation started or how long it lasted. The numbers cited in textbooks are based on models that fit the data, but other models with different parameters can also fit. Inflation is not a single theory. It is a framework, and within that framework there are dozens of variations, each with slightly different predictions. One of the biggest open questions is whether inflation left behind gravitational waves. General relativity predicts that rapid changes in space-time should produce ripples in the fabric of space itself, propagating outward at the speed of light. If inflation happened, it should have generated a background of primordial gravitational waves that would leave a faint imprint on the cosmic microwave background. In 2014, a team using the BICEP 2 telescope at the South Pole announced that they had detected exactly that signal. The news made headlines. The BBC called it the most compelling evidence yet for the faster-than-light expansion of the newborn universe. It looked like the smoking gun, proof that inflation was not just a good idea but a physical reality. Then the signal went away. Follow-up analysis showed that the detected pattern was consistent with dust in our own galaxy, not primordial gravitational waves. The claim was retracted, or at least downgraded to inconclusive. The search continues. Other experiments are looking for the same signal with better instruments and cleaner data. If they find it, and if the strength of the signal matches the predictions of a specific inflation model, that would be the closest thing to direct confirmation we are likely to get. But for now, the gravitational wave signature remains undetected. Still, inflation has become the standard story. Not because it is the only possible explanation for the flatness and horizon problems, but because it is the best explanation anyone has come up with. It fits the data, it makes testable predictions, it solves multiple puzzles with a single mechanism, and it does so without requiring absurd fine-tuning or appeals to coincidence. The universe is flat because inflation flattened it. The cosmic microwave background is uniform because inflation stretched a small thermalized region to cosmic size. The monopoles are missing because inflation diluted them, and the galaxies formed where they did because quantum fluctuations during inflation seeded the density variations that gravity turned into structure. There is something almost ridiculous about the whole picture, a field we have never seen, with a shape we can only guess at, sitting at a high energy state for a fraction of a second and then rolling downhill, stretching space by an unimaginable factor in the process. It sounds like something you would invent if you were writing science fiction and did not care whether the physics made sense. Except the physics does make sense. The math works, the predictions match the observations, and no one has come up with a better idea. Alan Guth, the physicist who introduced inflation, tells the story of realizing what the theory implied. He was working late one night in 1979, trying to solve the monopole problem, and he wrote down the equations for a universe where space was expanding exponentially. When he saw what the numbers were telling him, he wrote in his notebook, "Spectacular realization," and drew a box around it. That box is now famous. It sits in archives and textbooks and popular accounts as the moment inflation was born. Guth did not realize at the time that his solution to the monopole problem would also solve the horizon and flatness problems. That came later, when he and others worked out the full implications. But the core idea, the idea that the universe underwent a brief period of insanely fast expansion, driven by a scalar field in a false vacuum, came to him in a single night. It is one of the great examples of how science actually works. You start with a problem. You try different approaches. Most of them fail. Then you stumble on something that fits, and when you follow the logic all the way through, it explains more than you expected. Inflation was not designed to explain the flatness of the universe or the uniformity of the microwave background. It was designed to get rid of magnetic monopoles. The other explanations came along for the ride. That is how you know an idea has legs. It solves problems you did not even know you were asking it to solve. The universe, if inflation is right, did not start with the Big Bang. It started with a speck, a quantum fluctuation, a ripple in a field that had more energy than it should have. That ripple inflated, doubling in size again and again, faster than anything, until it was large enough to hold galaxies. Then the field decayed, the energy converted into particles, and the hot dense phase we call the Big Bang began. Everything you see, every star, every planet, every atom in your body, came from the energy released during reheating. But the stage itself, the space that holds it all, came from inflation, from a flash, from a moment so brief that calling it a moment is almost too generous. And yet that moment is why the universe is big enough for you to exist in. Why there is room for 100 billion galaxies, each with 100 billion stars. Why the sky is full of light and not just a single blinding point. Inflation gave the universe space, more space than it knew what to do with. And once that space was there, once the field had decayed and the particles had formed and the expansion had slowed to something more manageable, the universe could finally get on with the business of becoming the universe. The hard part was over. The stage was set. Now it just needed to fill it, and that is exactly what it did. Inflation gave the universe space, more space than it knew what to do with, and once that space was there, once the field had decayed and the particles had formed, and the expansion had slowed to something more manageable, the universe could finally get on with the business of becoming the universe. The hard part was over. The stage was set. Now it just needed to fill it. And that is exactly what it did. Except fill is the wrong word. The universe after inflation was not empty. It was full of energy. Enormous amounts of energy packed into a volume that was growing but still unimaginably hot. When the inflaton field decayed at the end of inflation, all the energy that had been driving the expansion had to go somewhere. It did not vanish. It converted. Energy became particles. The universe reheated and the temperature spiked to levels that make the core of a star look like a freezer. Estimates put the temperature at around 10 to the 27 Kelvin, though the exact number depends on the details of how inflation ended. That is hot enough that nothing we would recognize as matter could exist. No atoms, no nuclei, not even protons or neutrons, just a seething soup of fundamental particles and the forces that governed them. This is the universe 1 second after the Big Bang. Not 1 second after the initial singularity, if there ever was such a thing, but 1 second after reheating. 1 second after inflation ended and the hot dense phase began. And in that 1 second, more happened than in the billion years that followed. The 4 fundamental forces which had been unified during the Planck era split apart. Gravity separated first, sometime during or just after inflation. Then the strong nuclear force peeled off, leaving the electro-weak force to hold on a little longer before splitting into electromagnetism and the weak force. Each split was a phase transition, like water freezing into ice, except instead of molecules locking into a lattice, the universe was locking into the laws of physics we recognize today. The forces became distinct. The particles gained their identities. The rules of the game got written. At 1 second, the universe was filled with quarks, the building blocks of protons and neutrons, and leptons, which include electrons and neutrinos. But the quarks were not bound together yet. The temperature was too high. Quarks normally live inside protons and neutrons, held together by the strong force in groups of 3. But at temperatures above 1 trillion Kelvin, the strong force cannot keep them confined. The quarks swim freely in what physicists call a quark-gluon plasma, a state of matter so extreme that we have only been able to recreate it for microseconds in particle colliders. The entire universe was in that state. Every cubic centimetre of space was filled with unbound quarks, gluons, electrons, positrons, neutrinos and photons, all bouncing off each other in a chaos so dense that nothing could travel more than a few Planck lengths before colliding with something else. The universe was opaque. Not dark, because there was light everywhere, but opaque in the sense that light could not move freely. A photon emitted in one spot would immediately scatter off an electron or a quark and change direction. If you could somehow survive in that environment and open your eyes, you would see nothing but a uniform blinding glow in every direction. No shadows, no shapes, just heat. Then the universe expanded. Space stretched. The temperature dropped. And the first major transition happened. About 1 microsecond after reheating, the temperature fell below 1 trillion Kelvin, and quarks started binding together. The quark-gluon plasma condensed into protons and neutrons, the particles that would eventually form the nuclei of every atom in existence. This moment is called the quark epoch, and it marked the first time in the history of the universe that matter began to look like something we would recognize under a microscope. Protons and neutrons are stable. They do not decay on human timescales. Once they formed, they stuck around. The universe now had building blocks it could work with. But it still did not have atoms. Atoms require nuclei and electrons to bind together, and the universe was far too hot for that. Electrons were still zipping around at relativistic speeds, smashing into anything they came near. The photons, particles of light, were energetic enough to blast apart any atom that tried to form, so the universe stayed a plasma, a state where electrons and nuclei exist separately, and nothing is electrically neutral. This would last for a long time, hundreds of thousands of years. But before we get there, something important happened in the first few minutes, something that determined what the universe would be made of for the rest of its existence. Physicists call it Big Bang nucleosynthesis, and it is the process by which the first atomic nuclei were forged. At 1 second, the universe was too hot for nuclei heavier than a single proton, which is just hydrogen, the simplest nucleus possible. But as the temperature dropped, protons and neutrons began to stick together. Not into atoms, because electrons were still flying around freely, but into nuclei. The process started at about 10 seconds and lasted until roughly 20 minutes after reheating. That 20-minute window is one of the most important stretches of time in cosmic history because it determined the chemical composition of the universe. Everything that came later, every star, every planet, every molecule in your body, had to work with the raw materials that nucleosynthesis provided, and those materials were limited. The simplest reaction was the formation of deuterium, a heavy form of hydrogen with 1 proton and 1 neutron stuck together. Deuterium is fragile. At high temperatures, photons smash it apart as fast as it forms. But once the universe cooled below about 1 billion Kelvin, deuterium became stable enough to accumulate. And once you have deuterium, you can build heavier nuclei. 2 deuterium nuclei can fuse to form helium-3, which has 2 protons and 1 neutron. or they can fuse to form helium-4, the most common form of helium, with 2 protons and 2 neutrons. Helium-4 is unusually stable. Its binding energy is high, meaning it takes a lot of force to break it apart once it forms. And because the early universe was full of protons, neutrons and deuterium smashing into each other at high speeds, helium-4 formed in large quantities. By the time nucleosynthesis ended, about 25% of the universe's normal matter by mass had been converted into helium. The rest, about 75%, stayed as hydrogen. Trace amounts of lithium and beryllium also formed, but in such small quantities that they barely register. Anything heavier than lithium did not form at all during Big Bang nucleosynthesis. The universe was not hot or dense enough to fuse lithium into carbon or carbon into oxygen. Those elements would have to wait for the first stars. This 25 to 75 split, hydrogen to helium, is one of the key predictions of Big Bang cosmology, and it matches observations almost perfectly. When astronomers measure the chemical composition of old stars or gas clouds that have not been polluted by later generations of stars, they find roughly 25% helium and 75% hydrogen, exactly what the theory predicts. That agreement is not approximate, it is precise. And it is one of the main reasons cosmologists are confident the Big Bang model is correct. You cannot fake that kind of match by accident. The universe made a specific amount of helium in the first 20 minutes, and we are still finding that helium 13.8 billion years later. But nucleosynthesis did not give the universe atoms. It gave the universe nuclei, bare nuclei with no electrons attached. The universe was still too hot for electrons to stick. Photons were still energetic enough to ionize anything that tried to form a neutral atom. The result was a plasma that filled all of space, glowing white-hot, scattering light in every direction. This state persisted for a very long time, much longer than the few minutes it took to make the nuclei. The universe had to cool, it had to expand, it had to wait for the temperature to drop low enough that electrons could finally settle into orbit around the nuclei without being blasted off by radiation. That moment came about 380,000 years after reheating. Not 380,000 years after the Planck era, not after inflation, but after the hot dense phase began. 380,000 years is a long time by human standards. But in cosmic terms, it is a blink. The universe went from opaque to transparent in that window, and the transition changed everything. The transition is called recombination, which is a terrible name because it implies the electrons and nuclei were combined before and are now recombining. They were not. This was the first time they combined. But the name stuck, and now every cosmology textbook uses it. Recombination happened when the temperature of the universe dropped to about 3000 Kelvin, cool enough that electrons could bind to hydrogen and helium nuclei and stay bound. Once that happened, the universe became electrically neutral. There were no more free electrons flying around to scatter light. Photons, which had been bouncing off electrons for hundreds of thousands of years, were suddenly free to travel in straight lines. The universe went from opaque to transparent almost overnight. Not literally overnight, because there was no such thing as a day yet, but on cosmological timescales the transition was abrupt. And the light that was released at that moment, the light that had been trapped in the plasma, began a journey that would last for 13.8 billion years. That light is still travelling, and we can see it. It is called the Cosmic Microwave Background, the CMB, and it is the oldest light in the universe. Not the oldest light emitted by stars because there were no stars yet, the oldest light emitted by anything. When you point a radio telescope at the sky and tune it to microwave frequencies, you pick up a faint glow coming from every direction. That glow is the stretched and redshifted light from recombination. It has been travelling toward us for the entire history of the cosmos, and because the universe has been expanding that whole time, the light has been stretched. What started as visible and infrared light, with a temperature of 3000 Kelvin, has been pulled to longer and longer wavelengths until it now sits in the microwave part of the spectrum, with a temperature of about 2.725 Kelvin. That is cold. That is barely above absolute zero, but it is not zero, and the fact that it is not zero is one of the most important discoveries in the history of science. The CMB was predicted in 1948 by physicists working out the consequences of the Big Bang model. They realized that if the universe started hot and dense, it should have been filled with light, and that light should still be around today, cooled by expansion. But nobody took the prediction seriously enough to go looking for it. Then, in 1964, two engineers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were testing a radio antenna and kept picking up a persistent noise they could not get rid of. They checked for interference from New York City. They checked for radiation from the Milky Way. They even cleaned pigeon droppings out of the antenna in case that was somehow causing the signal. The noise did not go away. It was coming from everywhere, from every direction in the sky, day and night, summer and winter. A steady hum at a temperature of about 3 Kelvin. They had no idea what it was. Then they talked to a group of physicists at nearby Princeton who had just been discussing the possibility of detecting the CMB. The pieces clicked. Penzias and Wilson had accidentally discovered the afterglow of the Big Bang. They won the Nobel Prize for it in 1978. The CMB is not perfectly uniform. If it were, the universe today would not have galaxies or stars or planets. Everything would be spread out evenly, a thin gas filling infinite space with nothing clumping together. But the CMB has fluctuations, tiny variations in temperature, about 1 part in 100,000, spread across the sky in a pattern that looks random but is not. Those fluctuations are the seeds of structure. They are the fingerprints of the quantum fluctuations that got stretched during inflation. Regions that were slightly denser than average at the time of recombination show up as slightly warmer spots in the CMB. Regions that were slightly less dense show up as cooler spots. And when you map those temperature variations across the entire sky, you get a picture of the universe as it was 380,000 years after the Big Bang. A baby picture, the earliest snapshot of the cosmos we will ever have. Satellites have mapped the CMB with extraordinary precision. COBE, launched in 1989, was the first to detect the fluctuations. MAP, launched in 2001, measured them in detail. Planck, launched in 2009, refined the measurements to the point where cosmologists can extract more information from the CMB than from almost any other observation. The temperature variations, the statistical pattern of hot and cold spots, the geometry of the fluctuations, all of it matches the predictions of the Big Bang model with inflation. The universe is flat, or very close to flat, just as inflation predicts. The fluctuations are nearly scale invariant, just as inflation predicts. The overall temperature is 2.725 Kelvin, just as the Big Bang model predicts. The agreement is so tight that the standard model of cosmology, the lambda CDM model, can fit the CMB data with just 6 parameters, 6 numbers that describe the entire history and structure of the universe. That is not hand-waving, that is precision. The CMB also tells us when the universe became transparent. Before 380,000 years, the universe was opaque. You could not see across a room if rooms had existed. Light scattered constantly, trapped in the plasma. After recombination, the universe cleared. Light travelled freely. If you had been there at that moment, floating in space with a telescope, you would have seen a faint red glow in every direction as the last scattering surface, the moment when photons decoupled from matter, receded into the distance. Today that surface is 46 billion light-years away in every direction, because space has been expanding the whole time. We are sitting inside a sphere of light, the CMB, that marks the boundary of the observable universe. Everything beyond that boundary is hidden from us, not because the light has not had time to reach us, but because the light was emitted from regions of space that are now being carried away from us faster than light can travel. We will never see past the CMB. It is the edge of our view, the oldest signal we can detect, the moment when the universe first opened its eyes. After recombination, the universe entered what astronomers call the Dark Ages, not because it was evil or foreboding, but because there were no stars yet. The CMB faded as the universe expanded and redshifted, and for the next few 100 million years, space was truly dark. The gas was neutral, mostly hydrogen and helium, drifting in vast clouds. Gravity was at work, pulling denser regions together, but the process was slow. The first stars did not ignite until about 100 to 200 million years after the Big Bang. Nobody knows exactly when because we have not seen them yet. The James Webb Space Telescope is looking, pushing back to the earliest moments when starlight first appeared. But the very first generation of stars, the ones astronomers call population 3 stars, have never been directly observed. They are a prediction, a necessary step in the story, and they were monsters. Population 3 stars, if the models are right, were enormous, not 10 times the mass of the Sun, not 50. Some of them may have been 300 times the Sun's mass or more. They formed from pure hydrogen and helium, with no heavier elements to cool the gas and allow smaller stars to collapse. The result was stars that burned insanely hot, insanely bright, and died insanely fast. A star 300 times the Sun's mass might live for only a few million years before exhausting its fuel, and exploding in a supernova so powerful it could outshine an entire galaxy for weeks. And when those stars exploded, they seeded the surrounding gas with the first heavy elements: carbon, oxygen, nitrogen, iron, all the elements heavier than lithium. Those elements mixed into the next generation of gas clouds, and the next generation of stars that formed were smaller, cooler, more like the stars we see today. Population 2 stars, then population 1 stars, like the Sun, which formed in galaxies that had already been enriched by billions of years of stellar evolution. The first galaxies formed from the clumping of gas and dark matter in regions where the density was slightly higher than average. Dark matter, which does not interact with light but does interact through gravity, provided the scaffolding. It clumped first, forming halos that pulled normal matter inward. The gas fell into those halos, heated up, and eventually collapsed into stars. Small galaxies formed first, then merged into larger ones. The process is still ongoing. The Milky Way is currently in the process of absorbing several smaller galaxies, and in a few billion years it will collide with Andromeda, our nearest large neighbour. Galaxy formation is not a one-time event. It is a continuous process driven by gravity and the initial conditions set during inflation. The large-scale structure of the universe, the cosmic web of filaments and voids that you see when you map the positions of millions of galaxies, is a direct consequence of those initial fluctuations. The hot spots in the CMB, the regions that were slightly denser at recombination, became the filaments. The cold spots became the voids. Gravity pulled matter into the dense regions and the voids emptied out as galaxies fled toward the filaments. The result is a universe that looks like a sponge or a foam, with galaxies concentrated along thin sheets and filaments, and vast empty spaces in between. The pattern is not random, it is the amplified echo of quantum fluctuations from the inflationary era, blown up to scales of hundreds of millions of light years. And here is the part that ties it all together. The universe did not have a center. It did not expand from a single point into empty space. The Big Bang happened everywhere. Every point in space was part of the hot, dense state, and every point expanded. If you rewind the history of the cosmos, every galaxy, every star, every atom traces back to a time when it was packed together with everything else. But there is no location you can point to and say the Big Bang happened here. It happened here and there and everywhere. The expansion is not objects moving through space, it is space itself growing. The distance between galaxies increases not because they are flying apart, but because new space is appearing between them. That is what expansion means, and that expansion has been happening for 13.8 billion years, slowing for the first several billion as gravity tried to pull everything back together, then accelerating for the last several billion as dark energy, whatever it is, began pushing everything apart. The universe we live in is the product of that history. The hydrogen in your body was made in the first few minutes after the Big Bang. The carbon, nitrogen, and oxygen were made in the cores of stars that exploded billions of years ago. The iron in your blood was forged in a supernova. The calcium in your bones came from a different supernova. You are made of star stuff, as Carl Sagan liked to say, and that star stuff came from a universe that started as a speck of quantum foam, inflated to cosmic size in a flash, reheated into a plasma, cooled into nuclei, became transparent, collapsed into stars, and eventually assembled into planets and people. The whole sequence is written in the light we see today, in the CMB, in the spectra of distant galaxies, in the abundances of hydrogen and helium, in the structure of the cosmic web. The story is consistent. The pieces fit. And while there are still questions, enormous questions about dark matter and dark energy and quantum gravity, the broad outline of how the universe evolved from a hot, dense state to the cosmos we see today is not in doubt. It is tested. It is measured. It is as close to certain as science gets. But the story does not explain where the initial state came from. It does not tell you why there was a hot, dense phase in the first place. It does not tell you why the laws of physics are what they are or why the universe exists at all. Those questions sit outside the reach of observation. You cannot rewind the clock past the CMB. You cannot see past recombination. The universe before that moment is hidden behind a wall of opaque plasma, and the universe before the Planck era is hidden behind a wall of broken mathematics. So cosmologists do what scientists always do when they hit a wall. They build models, they make guesses, they try to find frameworks that might, if you squint hard enough, let you say something sensible about what came before, or whether before even makes sense. One of the strangest and most ambitious of those frameworks is called the no-boundary proposal, and it does not just tweak the story, it rewrites the rules. The universe, if inflation is right, did not start with the Big Bang. It started with a speck, a quantum fluctuation, a ripple in a field that had more energy than it should have. That ripple inflated, doubling in size again and again, faster than anything, until it was large enough to hold galaxies. Then the field decayed, the energy converted into particles, and the hot dense phase we call the Big Bang began. Everything you see, every star, every planet, every atom in your body, came from the energy released during reheating, but the stage itself, the space that holds it all, came from inflation, from a flash, from a moment so brief that calling it a moment is almost too generous. And yet that moment is why the universe is big enough for you to exist in, why there is room for 100 billion galaxies, each with 100 billion stars, why the sky's full of light and not just a single blinding point. But here is the problem. The story still has a gap. Inflation explains how the universe got large. It explains why it is flat and smooth and full of structure. It explains the patterns we see in the cosmic microwave background. But it does not explain where the inflaton field came from. It does not explain why there was anything to inflate in the first place. It pushes the origin question back one step, but it does not answer it. You are left asking the same question you started with, just in a different form. What came before inflation? What set the initial conditions? And if the answer is nothing, then what does nothing even mean in this context? For decades, physicists tried to work around that gap by treating the initial conditions as a given. You start with a universe in some state, you let the equations run forward, and you see what happens. The state itself, the thing you start with, is just a boundary condition, an input. You plug it in and move on. But some physicists were not satisfied with that. They wanted to know whether the initial conditions themselves could be explained, whether there was a way to describe the origin of the universe that did not require you to assume anything was already there. And in 1983, two physicists, Stephen Hawking and James Hartler, published a paper that tried to do exactly that. They called it the no-boundary proposal, and it is one of the strangest and most ambitious ideas anyone has ever put forward about the beginning of everything. The core idea is simple to state, though the mathematics behind it is anything but simple. Hawking and Hartley proposed that the universe has no boundary to its past, not in the sense that it stretches infinitely backward in time, but in the sense that time itself does not have an edge. There is no moment where time began, no first instant, no starting point where you can say this is where it all kicked off. Instead, time near the origin of the universe becomes something else. It blurs, it curves back on itself, it stops behaving like the straight timeline we are used to, and starts behaving like a surface. And on a surface, there is no edge unless you put one there. Hawking liked to explain this with an analogy. He would ask, what lies south of the South Pole? The question sounds reasonable. You can travel south from anywhere on Earth. But if you are standing at the South Pole itself, the question stops making sense. Every direction is north. South does not exist there, not because the maps are broken, but because you have reached the point where the framework no longer applies. The South Pole is not an edge. It is not a boundary. It is just a point on a surface that happens to be the southernmost point, but the surface itself continues in every direction. Asking what came before the Big Bang, Hawking argued, is like asking what lies south of the South Pole. The question assumes a framework, a concept of before, that might not apply. If time itself has a structure more like a sphere than a line, then the Big Bang is not the beginning of time. It is just the point where certain coordinates converge, and there is nothing on the other side because there is no other side. There is only the surface. That is the idea. The universe is finite in time, but it has no boundary. No edge where time stops or starts. It just is. And if that is true, then the whole question of what came before becomes meaningless. Not unanswerable in the sense that we do not have the data yet, but meaningless in the sense that the question is aimed at a target that does not exist. You're asking for a direction that is not there. The mathematical version of this idea is more technical, and it involves a concept called imaginary time. That phrase sounds like science fiction, and in a way it is, but it has a precise meaning in physics. In the equations of quantum mechanics, time is usually treated as a real number. 1 second is 1 second. It flows forward. It is the variable you use to track how a system evolves, but there is a trick used in certain calculations where you replace real time with imaginary time. You multiply the time variable by the imaginary number I, which is the square root of -1. That substitution changes the character of the equations. Instead of describing evolution forward in time, the equations start describing a kind of geometry, a shape. In the no-boundary proposal, Hawking and Hartley used this imaginary time trick to describe the very early universe. Near the origin, they said, time was not real in the usual sense, it was imaginary. And in that imaginary time framework, the universe did not have a sharp beginning. The singularity, the point of infinite density that general relativity predicts when you run the equations backward to time zero, gets smoothed out. It becomes finite, rounded. The geometry of space-time near the origin looks less like a cone with a sharp point and more like the rounded end of a sphere. There is no edge, no boundary, just a smooth surface that curves back on itself. This is not easy to picture. Your brain wants time to be a line, a sequence of moments stretching from the past into the future. But the no-boundary proposal says that picture only works after the universe has expanded and cooled enough for time to behave like a line. Before that, or rather in the regime where real time stops applying, time was part of the geometry. It was a dimension like the others, not fundamentally different from space. And in that regime, the universe had no boundary because space-time itself was closed, finite but unbounded like the surface of a sphere. The analogy Hawking used most often was the surface of the Earth. If you're standing on the ground, the Earth looks flat. It looks like it goes on forever in every direction. But if you zoom out far enough, you see that the surface is curved. It wraps around. If you walk in one direction long enough, you come back to where you started. The surface is finite. You can measure its area, but there is no edge, no boundary, no place where the surface stops. The no-boundary proposal says the universe is like that, except instead of a two-dimensional surface embedded in three-dimensional space, it is a four-dimensional space-time embedded in, well, nothing. It is not embedded in anything. It is just a geometry that exists on its own terms. One of the key implications of this idea is that the universe might not need an external cause. Most cosmological models, even the ones that include inflation, assume there was some initial state that got the ball rolling. Some set of conditions that existed at the beginning. The no-boundary proposal says there was no beginning in the usual sense. The universe did not start, it just is. Time does not extend infinitely into the past, but it also does not have a first moment. The geometry is closed, and because there is no boundary, there is no need for a boundary condition. No need to specify what things were like at time zero because time zero does not exist as a sharp point. It is smoothed out by the imaginary time framework into a region where the usual rules do not apply. Hawking was careful to say this was not the same as proving the universe was eternal. The universe in the no-boundary picture is finite in time. If you measure time in the usual way, starting from the moment when real time becomes well-defined, the universe has an age, 13.8 billion years give or take. But that age is measured from a point that is not a beginning. It is measured from the point where space-time transitioned from the imaginary time regime, where geometry dominated, to the real-time regime, where evolution and causality took over. The universe did not come from nothing in the sense of appearing out of a void. It came from a state where the concept of nothing does not apply because time and space were not yet separated into the framework we use to define existence. This is hard to wrap your head around, and Hawking admitted that. He once joked that when he tried to explain the no-boundary proposal to non-physicists, he could see their eyes glaze over the moment he mentioned imaginary time. But he insisted the idea was not just mathematical trickery, it was a way of describing the universe that took quantum mechanics seriously at the larger scales. General relativity, the theory that describes gravity and space-time, predicts singularities, points where the equations blow up and give nonsensical answers. Quantum mechanics, the theory that describes the behavior of particles and fields at the smallest scales, does not like singularities. It smooths them out. It introduces uncertainty and fuzziness. The no-boundary proposal is what you get when you try to apply quantum mechanics to the geometry of the universe itself. You get a picture where the Big Bang is not a singular event, but a smooth transition from one kind of space-time structure to another. The proposal also ties into inflation. In later work, Hawking argued that the no-boundary condition naturally leads to a period of exponential expansion. If you start with the geometry the no-boundary model predicts, and you let it evolve according to the laws of quantum field theory, the universe inflates. The inflaton field, or something like it, arises naturally from the boundary conditions. You do not have to put inflation in by hand. It emerges from the framework. That is a strong point in favour of the idea, though it is also one of the hardest parts to test. The mathematics is complex enough that extracting clear predictions is difficult, and the predictions that have been made are not always easy to compare with observations. The no-boundary proposal is speculative. It has to be. We do not have a complete theory of quantum gravity, the framework that would be needed to fully describe the regime where this proposal applies. String theory is one candidate for such a framework. Loop quantum gravity is another, but neither has been confirmed by experiment, and neither has produced a definitive version of the no-boundary idea that everyone agrees on. What Hawking and Hartle did was sketch a possibility, a way of thinking about the origin of the universe that does not require a first cause or a pre-existing state. Whether that possibility is the right one is still an open question. But the no-boundary proposal is not the only speculative idea about the origin and structure of the cosmos. Another framework, one that has gained a lot of attention in recent decades, takes the strangeness even further. It is called the holographic principle, and it suggests that the universe we live in might not be what it appears to be. Not in the sense that it is an illusion, but in the sense that the three-dimensional space we move through might be a kind of projection, a shadow cast by information encoded on a lower dimensional surface. If that sounds like science fiction, it is because it sounds exactly like science fiction. But it is also serious physics, backed by mathematical arguments that some of the best minds in the field take very seriously. The holographic principle grew out of work on black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that black holes have entropy. Entropy is a measure of disorder, or more precisely, a measure of how many different microscopic configurations a system can have while still looking the same macroscopically. A hot gas has high entropy because the particles can be arranged in many different ways and the gas still looks like a hot gas. A crystal has low entropy because the particles are locked into a specific arrangement. Black holes, Bekenstein and Hawking realized, have entropy proportional to the area of their event horizons. Not the volume inside the horizon, which is what you might expect, but the area of the two-dimensional surface that marks the boundary. That was strange. If a black hole's entropy is proportional to its surface area, that suggests the information about everything that falls into the black hole is somehow encoded on the horizon. Not inside the black hole, but on its boundary. It is as if the three-dimensional interior is described by a two-dimensional surface, a hologram. In a hologram, you shine light through a flat piece of film and a three-dimensional image appears. The three-dimensional structure is encoded in the two-dimensional film. The holographic principle says the universe might work the same way. The three-dimensional space we live in, and everything in it, might be encoded on a lower dimensional boundary. And the boundary, in the most radical versions of the idea, might be all that really exists. The principle was formalized in the 1990s by physicists like Gerard 't Hooft and Leonard Susskind. They argued that the maximum amount of information that can be stored in a region of space is proportional to the surface area of that region, not its volume. If that is true, then in some deep sense the interior of space is redundant. It is a projection, a way of describing information that is fundamentally stored on a boundary. The universe is a hologram, and we are part of the image. This idea is still highly speculative. Nobody has proven the holographic principle applies to the entire universe. The best evidence for it comes from a specific version of string theory, called AD-CFT correspondence, which describes a universe with a very different geometry from our own, a universe with a negative cosmological constant, which means space curves in a way that ours does not. In that setting, physicists have shown that the physics inside a volume of space can be exactly described by a theory living on the boundary of that space. The three-dimensional interior and the two-dimensional boundary are two ways of describing the same thing, and calculations done in the interior match calculations done on the boundary with perfect precision. That is not a loose analogy, it is an exact equivalence, proven mathematically for specific cases. But our universe does not have a negative cosmological constant. It has a positive one, which means space is accelerating apart, not curving inward. Whether the holographic principle applies to our cosmos is still an open question. Some physicists think it does. They argue that the principle is general enough to work in any space-time, and that the boundary for our universe might be the distant future, where the expansion has carried everything so far apart that space looks flat and empty. Others are more cautious. They point out that the AD-CFT correspondence, successful as it is a proof of concept, not a proof that holography is universal. If the holographic principle is correct, it has profound implications for the nature of reality. It would mean that space, the thing you move through every day, is not fundamental. It is emergent. It arises from information encoded on a boundary, the way a three-dimensional image arises from a two-dimensional hologram. Time might be emergent too, constructed from the way information on the boundary evolves. The particles and fields that make up matter and energy would be patterns in that information. Everything you think of as physical would be, in some sense, a projection. Not an illusion, because the projection is real and consistent and governed by laws but not fundamental. The real action, the real degrees of freedom, would live somewhere else, on the boundary, and the boundary might not even be a place in the usual sense. It might be a mathematical structure, a way of organizing information. The holographic principle is not part of the original no-boundary proposal. Hawking and Hartley did not invoke holography. They were focused on the shape of space-time near the origin of the universe, not on whether space itself is a projection. But the two ideas share a common theme. Both suggest that the universe is not what it appears to be on the surface. Both argue that the familiar concepts of space and time and causality might break down in extreme regimes, and that the real description of the cosmos might look very different from the everyday picture. And both are attempts to solve the same underlying puzzle. How do you describe the origin of the universe without assuming something was already there? The no-boundary proposal says you do it by erasing the boundary, by treating the origin not as a starting point but as a smooth feature of a closed geometry. The holographic principle says you do it by recognizing that the three-dimensional universe might not be the whole story, that the information describing the cosmos might live on a lower dimensional boundary, and the interior is just a convenient way of organizing that information. Neither idea has been proven. Neither has been tested directly. Both are frameworks, ways of thinking about the universe that might turn out to be right, or might turn out to be stepping stones towards something else. What makes these ideas significant is not that they are settled science, but that they show how far the field has come in asking the right questions. 50 years ago, cosmology was barely a science. It was a collection of observations and rough models with no clear way to test anything. Today, cosmologists have precise measurements of the cosmic microwave background, detailed maps of galaxy distributions, and theoretical frameworks that connect quantum mechanics to the geometry of spacetime. The no-boundary proposal and the holographic principle are products of that progress. They are not wild guesses. They are serious attempts to use the tools of modern physics to address questions that used to belong only to philosophy. But they leave something unresolved. Both frameworks describe the universe in ways that challenge the need for a first cause or a pre-existing state. But they do not explain why the universe exists at all. They do not tell you why there is something rather than nothing. They redefine the question, shift the ground under it, but the question remains. And some physicists have argued that the question can be answered more directly, not by appealing to imaginary time or holographic boundaries, but by showing that a universe can arise from a quantum vacuum, from nothing, in the only sense that nothing makes physical sense. That argument, and the controversy it sparked, is where the story goes next. But they leave something unresolved. Both frameworks describe the universe in ways that challenge the need for a first cause or a pre-existing state, but they do not explain why the universe exists at all. They do not tell you why there is something rather than nothing. They redefine the question, shift the ground under it, but the question remains. And some physicists have argued that the question can be answered more directly, not by appealing to imaginary time or holographic boundaries, but by showing that a universe can arise from a quantum vacuum, from nothing, in the only sense that nothing makes physical sense. That argument and the controversy it sparked is where the story goes next. Lawrence Krauss is not a quiet man. He is a theoretical physicist at Arizona State University, or was. depending on when you're reading this, and he has spent a significant portion of his career telling anyone who will listen that the universe did not need a creator. Not in the sense that he has a philosophical objection to the idea, though he might, but in the sense that the physics does not require one. The universe, he argues, can and likely did arise from nothing. Not nothing in some vague poetic sense, but nothing in the specific technical sense that physicists use when they talk about empty space. A quantum vacuum, the lowest energy state allowed by the laws of nature. And if you object that a quantum vacuum is not really nothing because it still has quantum fields and physical laws, Krauss will tell you that this is the only kind of nothing science can address. Anything beyond that is philosophy, and philosophy, in his view, does not get you very far when you're trying to explain where universes come from. He wrote a book about this in 2012. It is called A Universe from Nothing, and the title is not subtle. The cover shows a field of stars emerging from blackness, and the text promises to explain why there is something rather than nothing. The book became a bestseller. It also became a lightning rod. Physicists mostly liked it, or at least respected the attempt to bring cosmology to a general audience. Philosophers hated it. Theologians were split. Some saw it as a useful corrective to the idea that science has nothing to say about ultimate origins. Others saw it as a category error dressed up in equations, a bait and switch where the word nothing gets redefined halfway through the argument so that the conclusion sounds more impressive than it actually is. The core of Krauss's argument is straightforward. He starts by pointing out that the total energy of the universe might be zero, not approximately zero, exactly zero. That claim is not as strange as it sounds. Energy comes in different forms. There is the energy locked up in matter, which Einstein's famous equation E equals mc squared tells you is enormous. A single kilogram of matter contains about 9 times 10 to the 17 joules of energy, enough to power a small country for a year. Then there is kinetic energy, the energy of motion, and there is potential energy, the energy stored in fields and forces. Gravity, for instance, has potential energy. When you lift a rock off the ground, you are doing work against gravity, and that work gets stored as potential energy. Drop the rock and the energy converts back into motion. Gravitational potential energy is negative. That might sound like an accounting trick, but it is not. It is a consequence of how gravity works. Gravity is attractive. It pulls things together. To separate two objects that are gravitationally bound, you have to do work. You have to add energy to the system. That means the energy of the bound state is lower than the energy of the separated state. And if you define the energy of infinite separation as zero, which is a standard choice, then the energy of the bound state has to be negative. The deeper you fall into a gravitational well, the more negative the potential energy becomes. A planet orbiting a star has negative gravitational potential energy. A star in a galaxy has even more negative energy. And the universe as a whole, filled with matter pulling on other matter, has an enormous amount of negative gravitational potential energy. Krauss's key observation, which is not original to him, but which he explains more clearly than most, is that the negative energy from gravity might exactly cancel the positive energy from matter and motion. If you add up all the mass energy, all the kinetic energy, all the energy locked in fields and radiation, and then subtract the negative gravitational energy, this sum might be zero. Not because the universe is empty, but because the ledger balances. You have a universe full of stuff, but the stuff and the gravity pulling on the stuff cancel out. The total is nothing. That is the first clue, Krauss says, that a universe could come from nothing. If the total energy is zero, then the universe does not violate conservation of energy by existing. It does not need to borrow energy from somewhere else. It does not need an external source to provide the energy for all the matter and motion we see. The energy budget is balanced. The universe is, in a very real sense, free. Free in the economic sense. It costs nothing to make one. But that still leaves the question of how it got made. And this is where Krauss brings in quantum mechanics. Specifically, he brings in the uncertainty principle and the idea that empty space, the quantum vacuum, is not actually empty. This is the same quantum foam we talked about earlier. The same seething background of virtual particles popping in and out of existence, borrowing energy from the uncertainty principle, and paying it back before the universe notices. Krauss argues that if the total energy of a universe is zero, then the universe itself could be a quantum fluctuation, a big one, the biggest one possible, but still a fluctuation. still something that arises naturally from the properties of the vacuum without needing an external cause. Think of it this way. In the quantum vacuum, particles appear and disappear constantly. An electron and a positron pop into existence, exist for a tiny fraction of a second, and then annihilate. The process does not violate conservation of energy, because the particles do not last long enough for the energy debt to matter. The uncertainty principle allows it. Now scale that up. If the total energy of a universe is zero, or very close to zero, then the universe as a whole could appear as a fluctuation in the same way. It would not last forever in the sense that it would eventually expand and cool and thin out, but it would last long enough to become a universe, long enough for stars to form and galaxies to assemble, and people to show up asking where it all came from. The universe, Krauss says, is the ultimate free lunch. He goes further. He points to inflation, the period of exponential expansion we talked about earlier, and argues that inflation provides the mechanism that turns a quantum fluctuation into a lasting cosmos. Once a small patch of space starts inflating, it grows so fast that it becomes effectively permanent. The expansion creates more space, and the energy density driving the expansion stays roughly constant, so you get runaway growth. A fluctuation that might have collapsed back into the vacuum instead inflates into something large and stable. And once inflation ends and the energy converts into particles, you have a hot, dense universe ready to evolve into everything we see today. In public talks, Krauss is even more direct. He says that modern cosmology and particle physics show that the universe can arise from nothing without supernatural shenanigans. Those are his words, supernatural shenanigans. He is not interested in being diplomatic. He is making the case that the origin of the universe is a physics problem, not a theological one, and that physics has made enough progress to sketch an answer. You do not need a god to light the fuse. You do not need a first cause sitting outside the universe pulling strings. You just need quantum mechanics and gravity and a vacuum that obeys the laws we have already measured in labs. The rest follows. The reaction was predictable. Physicists who work in cosmology mostly nodded along. They know the arguments. They have heard versions of this story in seminars and read versions of it in papers. The details vary depending on which model of inflation you use and how you handle the quantum gravity regime. But the broad outline is standard. A universe with zero total energy can fluctuate into existence. Inflation can stabilize it. The laws of physics do the rest. Nothing about that requires new physics or wild speculation. It is a straightforward application of known principles to the most extreme situation imaginable. Philosophers, on the other hand, were not impressed. The objections started almost immediately, and they have not stopped. The central complaint is that Krauss is playing word games with the term nothing. He says the universe came from nothing, but what he actually means is that it came from a quantum vacuum. And a quantum vacuum is not nothing. It is a state with properties. It has quantum fields. It has energy fluctuations, it obeys laws, it has structure. Calling that nothing is like calling an empty room nothing, and then pointing out that the room still has walls and a floor and air and gravity. You have removed the furniture, but you have not removed the room. And the room is something. David Albert, a philosopher of physics at Columbia, wrote a scathing review of Krauss's book in the New York Times. He said Krauss was equivocating. He was using the word nothing in two different senses, and the argument only works if you do not notice the switch. In the conclusion, Krauss wants you to think he has explained how the universe arose from absolute nothingness, from the complete absence of anything. But in the body of the book, he is actually describing how a universe can arise from a quantum vacuum, which already presupposes the existence of space, time, quantum fields, and physical law. That is not explaining how something came from nothing. That is explaining how something came from something else. And the something else, the vacuum, is not philosophically nothing. It is a very specific physical state with very specific properties. Albert's review was harsh, and Krauss did not take it well. He responded, Albert responded back, and the whole thing turned into a public spat that made it clear the two sides were not going to agree. The physicists thought the philosophers were being pedantic, quibbling over definitions when the science was clear. The philosophers thought the physicists were being sloppy, ignoring the actual question by redefining the terms, and both sides had a point. Krauss is absolutely right that you cannot do science without starting from some framework. You need laws, you need fields, you need a structure to work within. If you strip all of that away, If you demand an explanation that starts from literal nothingness, with no laws and no structure and no properties at all, then you're asking for something science cannot provide. Science describes how systems behave. It does not explain why there is a system in the first place. But the philosophers are also right that Krauss is overselling the conclusion, saying the universe came from nothing in the headline, and then explaining in the details that it came from a quantum vacuum is misleading. It makes it sound like the problem is solved, when really all you have done is pushed it back one step. Now you have to explain where the quantum vacuum came from. Why does it have the properties it has? Why do the laws of physics take the form they do? Why is there a quantum mechanical framework at all, instead of some other framework or no framework? Those questions do not go away just because you have explained how a universe can fluctuate into existence, given that a vacuum already exists. The debate predictably has gone in circles for over a decade. Neither side has budged. Krauss still gives talks where he says the universe came from nothing, and philosophers still write papers pointing out that his nothing is not really nothing. The argument has become a kind of performance. Everyone knows the lines, everyone knows the rebuttals, and yet it keeps happening because the underlying tension is real. Science and philosophy are asking different questions, and both questions matter. Science wants to know how the universe works. Philosophy wants to know why there is a universe at all. And the two questions do not have the same answer. But Krauss's argument, for all the controversy it has generated, is not the end of the story. It is a bridge. A way of moving from the specific question of how our universe began to the much larger question of whether our universe is the only one. Because if a universe can fluctuate into existence from a quantum vacuum, and if inflation can stabilize that fluctuation, then there is no reason to think it happened only once. Inflation, according to many models, does not stop. It keeps going. Different regions of the inflating space stop inflating at different times, and each region that stops becomes a universe. A separate bubble of space-time with its own Big Bang, its own stars, its own galaxies. Our universe would be one bubble in an infinite froth. One outcome in a process that has been running forever and will keep running forever. This is the multiverse. The multiverse is not a single idea. It is a family of ideas, and the details depend on which model you use. But the core concept is simple. If inflation is eternal, and many models suggest it is, then the process of creating universes never stops. Inflation is always happening somewhere, and every time a region stops inflating, it becomes a new universe. Those universes do not interact. They are causally disconnected. Light from one can never reach another because the space between them is still inflating faster than light can travel. But they are all out there, each one a cosmos in its own right, each one with its own laws or at least its own constants, each one potentially very different from ours. This is not science fiction. This is a prediction that comes out of inflationary cosmology when you take the model seriously. Alan Guth, the physicist who introduced inflation, is on record saying that once inflation starts, it is hard to turn off. The field that drives inflation can decay in some regions, ending inflation locally and creating a universe, but in other regions the field keeps inflating. And because the space is expanding exponentially, the inflating regions grow faster than the non-inflating regions can eat into them. The result is eternal inflation, a state where inflation never fully ends. It just creates bubble universes continuously, each one a pocket of space where inflation has stopped and physics as we know it can operate. If that picture is right, and it is consistent with the math, though not yet confirmed by observation, then our Big Bang was not the beginning of everything. It was the beginning of our bubble, the moment when our patch of space exited the inflationary phase and reheated into a hot, dense state. But other patches exited at other times, or have not exited yet, or will exit in the future. The multiverse is not a thing that exists at one moment in time, it is a process, an ongoing cascade of universe creation driven by quantum fluctuations and eternal inflation. One of the most intriguing aspects of the multiverse is that it might explain why our universe looks the way it does. Specifically, why the constants of nature have the values they have. The strength of gravity, the mass of the electron, the charge of the proton, the rate at which the universe is expanding. All of these are free parameters in the standard model of physics. The equations do not tell you what their values should be. You have to measure them, and when you measure them, you find that they are finely tuned in a way that seems almost suspicious. Change the strength of gravity by a few percent and stars cannot form. Change the mass of the electron and atoms fall apart. Change the expansion rate and the universe either collapses before stars ignite or expands so fast that matter never clumps into galaxies. The range of values that allow for a universe with structure, with chemistry, with life, is extremely narrow. For decades, this fine-tuning was seen as a puzzle. Some people argued it was evidence of design, that the constants were set by something that wanted life to exist. Others argued it was just a brute fact, that the constants are what they are and asking why is pointless. The multiverse offers a third option. If there are many universes, each with different constants, then most of them will be lifeless. Most will be too hot or too cold or too empty or too chaotic to support anything like stars or planets or chemistry. But a few, purely by chance, will have constants that fall in the narrow range where structure can form, and those are the universes where observers can exist, where life can evolve, where someone can eventually ask why the constants are what they are. The answer is selection bias. We live in a universe with the right constants, because we could not live in a universe with the wrong ones. The other universes are out there, but they are empty. We do not see them because there is no one in them to do the seeing. This is called the anthropic principle, and it is one of the most controversial ideas in cosmology. Not because the logic is flawed, but because it feels like giving up. It feels like saying the constants are what they are because if they were not, we would not be here to notice. That is true, but it does not feel like an explanation. It feels like a tautology. And yet, if the multiverse is real, if there are billions or trillions or infinite universes out there with different constants, then the anthropic principle is not a cop-out. It is a statistical prediction. Most universes are lifeless. Ours is not. End of story. The multiverse also blurs the line between nothing and everything in a way that is deeply unsettling. If inflation is eternal, then the process of creating universes has been going on forever and will continue forever. There is no beginning to the multiverse as a whole, even if each individual universe has a beginning. The structure is infinite in time and infinite in space. Every possible configuration of constants, every possible initial condition, every possible history gets realized somewhere. There is a universe where you exist but made a different choice this morning. There is a universe where the Earth never formed. There is a universe where the laws of physics are so different that matter as we know it cannot exist. And there is no privileged universe, no central bubble, no special status for ours. We are one outcome in an infinite ensemble, no more significant than any other. That picture is hard to reconcile with the intuition that the universe should be unique, that there should be one set of laws, one history, one cosmos. The multiverse says no. It says the thing we call the universe is just a local patch of a much larger structure, and that structure does not care about us. It does not care about anything. It is just a consequence of inflation and quantum mechanics, churning out universes the way a factory churns out widgets. Krauss calls this the ultimate free lunch, but the multiverse makes it sound more like an all-you-can-eat buffet that never closes. Universes on demand, infinite variety, no bill. The catch, and it is a big one, is that we cannot test this, not directly. The other universes, if they exist, are beyond our horizon. We cannot see them. We cannot visit them. We cannot send signals to them or receive signals from them. The space between bubbles is inflating faster than light, which means the causal connection is severed. Anything that happens in another universe stays in that universe. We are stuck in ours. So the multiverse, for all its mathematical elegance and for all the ways it solves problems like fine-tuning, is not an observation. It is an inference, a prediction that comes out of inflationary models when you run them forward. And predictions that cannot be tested are, by definition, not science in the strict sense. They are speculation, informed speculation, built on solid physics, but speculation nonetheless. Some physicists are fine with that. They argue that if inflation predicts eternal inflation, and if eternal inflation predicts a multiverse, then the multiverse is as real as any other consequence of a successful theory. You do not need to observe every electron in the universe to believe that electrons exist. You just need a theory that predicts electrons and observations that confirm the theory. The multiverse, they say, is the same. It is a prediction. If the theory is right, the multiverse is real, whether or not we can see it. Other physicists are more cautious. They point out that science has always been about making predictions you can test, and if the multiverse cannot be tested, then it is not clear it belongs in the same category as, say, the existence of Neptune, which which was predicted by math and then observed through a telescope, the multiverse might be real, but calling it real without evidence is a departure from the way science has traditionally worked. The debate over the multiverse is in some ways a replay of the debate over Krauss's nothing. It is a fight over definitions and boundaries, over what counts as science and what counts as philosophy, over whether you can claim to have explained something when the explanation invokes structures and processes that are, by definition, beyond the reach of observation. And as with the nothing debate, both sides have legitimate points. The multiverse is a consequence of taking inflation seriously. But it is also a consequence that we might never be able to confirm, and that leaves the field in a strange place. Cosmology, which started as the study of the one universe we can see, has evolved into a framework that predicts many universes we cannot see. And the question of whether that evolution represents progress or overreach is still open. What is clear is that the questions have gotten bigger. Krauss wanted to explain how a universe could come from nothing. The multiverse framework says that if one universe can come from nothing, then infinite universes can come from nothing. And if infinite universes exist, then the question of why this universe exists stops being interesting. The interesting question becomes why anything exists at all. Why is there a multiverse? Why is there a quantum vacuum? Why are there laws that allow inflation and fluctuation and bubble formation? And those questions, as Krauss himself admits, are not questions physics can answer. Not yet. Maybe not ever. Because every answer you give just pushes the question back one more step. And at some point, you run out of steps. You hit the edge of the map. The place where what exists and why it exists blur into a single unanswerable knot. And that knot, that final question, is where the story has been heading all along. And those questions, as Krauss himself admits, are not questions physics can answer. Not yet. Maybe not ever. Because every answer you give just pushes the question back one more step. And at some point, you run out of steps. You hit the edge of the map. The place where what exists and why it exists blur into a single unanswerable knot. And that knot, that final question, is where the story has been heading all along. So let's take a breath. Let's step back and look at what we have actually learned. Not what we wish we had learned, not what the headlines promised, but what the science, the math, the observations, and the honest admission of limits actually tell us about where everything came from. Because after tracing the universe backward through 13.8 billion years of expansion, through the formation of galaxies and stars, through the transparent moment when the cosmic microwave background was released, through the forging of the first nuclei, through the quark-gluon plasma, through reheating, through inflation, through the Planck era, all the way back to the quantum foam and the no-boundary proposals and the arguments over what nothing even means, we're left with something that is not quite an answer. It is more like a map of how far we have come and how much further we still have to go. Here is what we know for certain. The universe has not always looked the way it does today. 100 years ago, most scientists believed the cosmos was static, eternal, unchanging. The stars were fixed in the firmament. The galaxies, though no one called them that yet, were islands scattered through infinite space, and time stretched infinitely in both directions. There was no beginning. There was no evolution. The universe simply was, and it had been that way forever. Then Edwin Hubble pointed a telescope at distant galaxies and noticed they were moving. Not drifting randomly, but fleeing. Every galaxy he looked at was rushing away from every other galaxy, and the farther away a galaxy was, the faster it appeared to be receding. That single observation, confirmed and refined over decades, shattered the static picture. The universe was not eternal and unchanging. It was expanding. It was evolving. It had a history. If you run the expansion backward, everything converges. The galaxies get closer. The temperature rises. The density increases. Go back far enough and you reach a state so hot and so dense that nothing we would recognize as matter could exist. That state is what we call the Big Bang, though the name is misleading. It was not an explosion in space. It was the expansion of space itself, carrying energy and matter along with it. And it happened, according to the best measurements we have, about 13.8 billion years ago. 13.787 billion years if you want the number the Planck satellite gave us, with an uncertainty of about 20 million years. That is the age of the universe. Not the age of the Earth, not the age of the Sun, Not the age of the Milky Way, the age of everything, the time since the expansion began, but knowing the age does not tell you what came before. And this is where the certainty ends and the speculation begins. Scientists can model the universe back to about 1 second after the expansion started. They can tell you what the temperature was, what particles existed, how the forces behaved. They can model it back to fractions of a second, back to microseconds, back to the moment when quarks first bound together into protons and neutrons. They can push further, back to the inflationary epoch when space itself expanded faster than light, stretching a region smaller than a proton into something large enough to contain the observable universe. They can even sketch what might have happened during the Planck era, the first 10 to the negative 43 seconds, when the universe was so small and so dense that quantum mechanics and gravity tangled together and the usual rules stopped applying. But they cannot go all the way back. The math breaks down, the equations fill with infinities. The concepts of space and time themselves become uncertain, blurred by quantum effects that we do not yet know how to handle. Stephen Hawking's no-boundary proposal tries to smooth out the singularity by treating time near the origin as imaginary, a mathematical trick that turns the sharp beginning into a rounded surface with no edge. Lawrence Krauss argues that the universe could have arisen as a quantum fluctuation in a pre-existing vacuum, a free lunch made possible by the fact that the total energy might be exactly zero. The multiverse picture suggests that our Big Bang was just one bubble in an eternal process of universe creation, driven by inflation that never fully ends. These are not wild guesses. They are serious attempts by serious physicists to use the tools they have to address the question of ultimate origins. But none of them are proven. None of them can point to a piece of data and say this confirms it. They are frameworks, possibilities, the best we can do with the information we have. And here is the uncomfortable truth. Every one of those frameworks starts with something. Hawking's no-boundary proposal assumes the laws of quantum mechanics. Krauss's vacuum fluctuation assumes a quantum vacuum with specific properties. The multiverse assumes inflation and the fields that drive it. None of them start from nothing in the absolute philosophical sense. They start from a state with rules, with structure, with the potential to evolve into something more complex. And that means the ultimate question, the question of why there is something rather than nothing, has not been answered. It has been rephrased. We have traced the universe back to a state that looks a lot like nothing, a quantum foam with no particles and no structure and no fixed geometry, but that state still has properties. It still obeys laws, it is still something, and the question of where those laws came from, why they take the form they do, why there is a framework at all, remains untouched. Some physicists argue this is as far as science can go, that asking what came before the laws of physics is like asking what is north of the North Pole. The question assumes a framework that does not apply. The laws are not things that came from somewhere, they are the structure that allows anything to come from anywhere. Without them, the concept of causality does not exist. Without them, the word before has no meaning, so demanding an explanation for the laws themselves is demanding an explanation that cannot exist, because explanation is a concept that only makes sense within the framework the laws provide. If that sounds like a dodge, like scientists refusing to answer the hard question, consider what the alternative would require. To explain the laws, you would need a meta-law, a rule that tells you why the laws are what they are, but then you would need to explain the meta-law, and the meta-meta-law, and so on forever. At some point you have to stop. You have to accept that there is a baseline, a foundation, a set of principles that simply are. And for physics, that baseline is the laws of nature. They are what the universe does. Asking why it does that instead of something else is asking a question that may not have an answer, because the structure of answers depends on the laws already being in place. Philosophers are not satisfied with that. They point out that even if science cannot explain the laws, the question is still meaningful. Why are there laws at all? Why is there a universe governed by rules instead of no universe at all? And if the answer is that the universe just is, that existence is a brute fact with no further explanation, then science has not solved the mystery. It has just moved the mystery to a place where science cannot reach. That is fair. It is an honest objection. And it highlights the boundary between what science can do and what philosophy asks. Science describes how things work. It builds models, makes predictions, tests them against observation. It is extraordinarily good at that. It has taken us from a static eternal cosmos to a dynamic evolving universe with a precise age and a detailed history. It has shown us quantum foam and inflation and the cosmic microwave background. It has measured the expansion rate to fractions of a percent. It has mapped the large-scale structure of space and traced the formation of the first stars. That is not nothing. That is an achievement on a scale that would have been unimaginable a century ago. But science does not, and probably cannot, answer the question of why there is a stage for all this to happen on. Why there is a universe instead of no universe. And that question, the ultimate why, is the one that refuses to go away. It sits at the end of every explanation like a weight you cannot lift. You can describe how the universe evolved from a hot, dense state. You can show how that state might have arisen from a quantum fluctuation. You can argue that the fluctuation was allowed by the uncertainty principle and stabilized by inflation. You can invoke the no-boundary proposal to eliminate the need for a beginning. You can appeal to the multiverse to explain the fine-tuning of constants. And when you are done, when you have traced every step and shown every connection, the question is still there. Why? Some people find that frustrating. They want closure. They want an answer that feels complete. Others find it liberating. They see the persistent mystery as a reminder that the universe does not owe us comprehensibility, that reality is under no obligation to make sense in human terms, and still others see it as evidence that there is something beyond the physical, something that science by its nature cannot touch. A first cause, a necessary being, a ground of existence that sits outside the causal chain and does not need an explanation because it is the explanation. That is theology, not science, and whether you find it persuasive depends on factors that have nothing to do with the data. But the fact that the question remains open, that science has not closed the gap, means the conversation is not over. It is ongoing, and it will probably continue as long as there are people capable of asking why. Here is what strikes me as the most unsettling part of this whole story. The question itself might be the most important thing, not the answer. The question, because the act of asking where everything came from, of tracing the universe back through time and space and energy and quantum foam, is what drove the discoveries. It is what pushed Hubble to measure the redshifts of galaxies. It is what led Penzias and Wilson to discover the cosmic microwave background. It is what motivated Guth to invent inflation and Hawking to propose the no-boundary condition. It is what drives physicists to build particle accelerators and launch space telescopes and spend years analysing data that most people will never see. The question is the engine. The curiosity is the fuel. And the fact that the answer keeps receding, that every new layer of understanding reveals another layer of mystery beneath it, does not make the pursuit pointless. It makes it endless. And maybe that is the point. We live in a universe that emerged from something we still do not fully understand. Something that looked like nothing, or maybe was nothing in some deep sense we have not yet grasped. It expanded faster than light for a fraction of a second, inflating from a speck smaller than an atom to something vast enough to hold galaxies. It cooled and condensed and formed particles and nuclei and atoms. It became transparent. Light travelled freely for the first time. Stars ignited, galaxies assembled. Heavy elements were forged in the cores of dying suns and scattered into space by supernovae. Planets formed from the debris. Chemistry happened. Life emerged. Evolution shaped that life into beings capable of looking up at the night sky and asking where it all came from. And the answer those beings have pieced together, over centuries of observation and argument and experiment, is that the universe has a history, a trajectory, a story that begins, as far as we can tell, about 13.8 billion years ago. Not in a place, because there was no place yet. Not at a time, because time itself might not have existed in the way we understand it, but in a state, a condition, a moment of transition from something we cannot describe to something we can. That is the shift. That is the revolution. 100 years ago, the universe was eternal and static. Today, it is dynamic and evolving, with a definite age and a clear trajectory from simplicity to complexity. That shift is not a small adjustment. It is a complete rewrite of humanity's place in the cosmos. We are not living in an unchanging backdrop. We are living in a universe that had a beginning, that has been changing ever since, and that will continue changing long after we're gone. The stars will burn out, the galaxies will drift apart. The expansion will accelerate until every galaxy beyond our local group is so far away that its light will never reach us. Eventually, in trillions of years, the universe will be cold and dark and empty. A thin soup of particles spread across infinite space, with nothing left to power the reactions that make stars shine or life persist. That is the trajectory. That is where the story leads. And knowing that, feeling the weight of it, changes the way you think about existence. Because it means the universe is not a container. It is an event, a process, a temporary arrangement of matter and energy that arose from conditions we are still trying to map and will eventually dissolve into conditions we can predict but cannot stop. You are part of that process. So is the Earth, the Sun, the Milky Way, every galaxy in the observable universe. All of it is transient. All of it came from something else and will become something else. The atoms in your body were forged in stars that exploded billions of years ago. The oxygen you breathe, the carbon in your cells, the calcium in your bones, all of it was made in the cores of massive stars and scattered into space when those stars died. You are made of star stuff, and that star stuff came from a universe that began as a quantum fluctuation, or a smooth no-boundary geometry, or a bubble in an eternal multiverse. The chain goes back further than you can trace, and the fact that it goes back at all is the thing that makes the question so compelling. The ultimate answer might be that nothing never truly existed, that what we call nothing, the quantum vacuum, the state of lowest energy, is still something. It has fluctuations, it has potential, it has the seeds of universes built into its structure. And if that is true, then the transition from nothing to something is not a transition at all. It is just a rearrangement, a reshuffling of energy and information into a form that allows stars and planets and people. The universe did not come from nowhere. It came from a state that was always capable of producing universes, and the only reason we think of that state as nothing is because it does not have the features we associate with something. No particles, no structure, no galaxies or stars or solid ground. But it has rules. It has fields. It has the capacity to evolve, and that capacity is not nothing. It is the potential for everything. That is the unsettling truth. The question that created everything, the question of where it all came from, might not have a final answer because the question assumes a starting point that does not exist. The universe might not have started. It might have transitioned. It might have emerged. It might have always been in some form, cycling through states we cannot yet describe. Or it might be one outcome in an infinite ensemble of outcomes, no more special or significant than any other. The multiverse, if it is real, erases the uniqueness of the Big Bang. It makes our universe just one bubble in a foam that has no beginning and no end. And if that is the case, then the question is not why did the universe begin, but why does anything happen at all? Why is there a process? Why is there change? Why is there a framework that allows states to transition into other states instead of a static, unchanging void? And that question, the deepest one, the one that sits beneath all the others, is not going away. It will keep driving the research. It will keep pushing scientists to build better instruments, refine the models, test the predictions. It will keep philosophers arguing about definitions and boundaries. It will keep theologians and poets and curious people everywhere staring at the night sky and wondering. Because the universe, whatever it is, did not wait for us to understand it before deciding to exist. It is here. You are here. And the fact that you can ask where it came from, that you can trace the story back through time and space and quantum foam and wrestle with the limits of language and knowledge, is part of the process. You are the universe asking questions about itself, and the questions do not stop. They grow, they deepen, they lead to new discoveries and new mysteries and new reasons to keep looking. So where does that leave us? With a universe that is 13.8 billion years old, give or take 20 million. With a history that stretches from a hot, dense state to the vast, cold cosmos we see today. With a framework that describes how galaxies formed, how stars ignited, how atoms assembled, how life emerged. With a map that goes back almost to the beginning, but not quite all the way. With models that sketch what might have come before but cannot prove it. With a question that refuses to close and a mystery that grows larger the more we learn. And with the uncomfortable recognition that the ultimate answer, if there is one, might be forever out of reach. Not because we are not smart enough, not because we lack the tools, but because the question itself might be pointing at something that lies beyond the boundary of what questions can do. That is not a failure. That is the human condition. We are finite beings trying to understand an infinite cosmos. We are brief flickers of consciousness in a universe that will outlast us by trillions of years. We are made of atoms that were forged in stars, governed by laws we did not choose, asking questions that might not have answers, and yet we keep asking. We keep building telescopes and accelerators. We keep refining the models. We keep pushing at the edges of the known, not because we expect to reach the end, but because the act of pushing is what makes us human. The curiosity is the point, the wonder is the reward, and the fact that the universe surprised us, that it turned out to have a beginning and a history and a trajectory we can measure, is reason enough to keep going. Because every answer we have found has made the universe stranger, not simpler. Quantum mechanics is strange. Relativity is strange. Inflation is strange. The cosmic microwave background is strange. The accelerating expansion is strange. Dark matter and dark energy are strange. The multiverse, if it exists, is strange. And the strangeness does not go away when you get used to it. It deepens. It becomes more layered. It opens new questions faster than it closes old ones. And that is what makes cosmology, the science of the universe's origin and evolution, one of the most exciting fields in all of human inquiry. Because the story is not over, the map is not complete, the final chapter has not been written. We are living in the middle of the greatest mystery there is, and the fact that we can participate in unraveling it, even a little, even at the edges, is a privilege that should not be taken lightly. So the unsettling truth is this: the universe came from something we call nothing, because we do not have a better word. It evolved through stages we can model with precision back to fractions of a second after it began. It inflated, reheated, cooled, condensed, and became the cosmos we see today. And the question of why any of that happened, why there is a universe at all instead of an eternal unchanging void, remains open. Science has taken us further than anyone thought possible a century ago. It has shown us the shape of the cosmos, the age of everything, the structure of space and time and matter. But it has not, and might never, answer the ultimate why. And that is okay, because the pursuit of that answer has given us everything else. The knowledge, the wonder, the humility that comes from realizing how small we are and how vast the mystery is. The question created everything we know, and it will keep creating, because as long as there are minds capable of asking, the question will remain, and the universe, indifferent and magnificent, will keep unfolding its secrets one discovery at a time. So here is where we stand. After tracing the universe backward through 13.8 billion years of expansion, after peeling back layer after layer of reality until the laws themselves started to blur, after wrestling with quantum foam and imaginary time and the stubborn refusal of nothing to stay empty, we arrive not at an answer but at a threshold, a place where the tools we built to understand the cosmos finally admit they cannot go any further. Not because the tools are broken, because the question might be, and maybe that is the point. Maybe the deepest truth about existence is not that it came from something or nothing, but that it came from a framework so alien to human intuition that the words we use to describe it, before, nothing, beginning, are just approximations. Placeholders for concepts our language was never designed to hold. The universe does not owe us a story that makes sense. It does not owe us closure. It is under no obligation to fit inside the categories we invented to navigate a world of objects and time and cause and effect. And yet it let us get this far. It let us measure its age to within 20 million years. It let us map the afterglow of its infancy. It let us trace structure back to quantum fluctuations smaller than an atom. That is not nothing. That is astonishing. You are standing on a planet made of dead stars, inside a galaxy that formed from seeds planted during a moment of exponential expansion, asking questions about an origin that might not exist in the way you think it does. And the fact that the question remains unanswered does not diminish what you have learned. It expands it. Because every answer we have found has made the universe larger, stranger, and more beautiful than we expected. And the next answer, if we ever find it, will do the same. Keep looking up and keep asking careful questions, because every new measurement may change the meaning of the oldest mystery.